In this lesson, we want to talk about one-to-one functions and the horizontal line test. So in this section of our course, we're going to be talking about exponential and logarithmic functions. But before we can get to these topics, we need to first discuss one-to-one functions and also inverse functions. So today, we're going to talk about one-to-one functions and our horizontal line tests. And then in the next lesson, we'll kind of follow up and we'll look at some algebraic methods. And then we'll move on to inverse functions and then exponential functions and logarithmic functions. All right, so let's start out with just a brief review of functions in general. This is something we covered in depth earlier in the course. So we already know that a function is a special type of relation where each member of our domain, or x value, corresponds to one and only one member of the range, or y value. So for example, if we look at this f here, this is a relation, and it's also going to be a function, and it just consists of these four ordered pairs. So we have 3, 2, 1, -9, 7, 4, and 2, 2. So how do we know if this is a function? Again, with this type of simple example, you would go through and you would look for a duplicate x value, right? Because if you had a duplicate x value, that means that that given x value is associated with more than one y value. Now, we can also look at the mapping diagram, and we can see that an x value of 3 is associated with a y value of 2, an x value of 1 is associated with a y value of -9, an x value of 7 is associated with a y value of 4, and then an x value of 2 is associated with a y value of 2. Now, the reason I chose this as example is because it's going to relate to something in a minute, and also we need to remember that this part right here does not break, or you could say does not violate the definition of a function. I can have a y that is associated with two different x values. That's not an issue. With a function, if I give you something as an input or as an x value, it has to give me as an output or as a y value a unique value. So if I said, hey, what is y when x is 3? Well, we know it's going to be 2, right? If I go to this ordered pair, if x is 3, y is 2. If x is 3, y is 2. Then additionally, if I said, hey, what is y when x is 2? Well, it's going to be 2, right? If x is 2, y is 2. So there's a clear association there. There's an answer. If I said, hey, if x is this, what's y? There's a clear answer. Now, if we look at something that's not a function, you're going to have a situation where there's not a clear answer, not a clear association between an x value and a given y value. So let's look at g. G is a relation and it's not a function. And again, the easy way to look at this is you look for duplicate x values. You have -1, 3, 2, -5, -1, 7, and 4, 6. You've got that -1 that occurs twice, so that's a red flag that this is not a function. And again, when you look at the mapping diagram, you see that -1, this x value, corresponds to 3, that y value, and 7, that y value. So if I said, hey, what is y when x is -1? You don't know whether to answer 3 or to answer 7. So this guy is not a function. Now, when we talk about a one-to-one function, this is a stricter definition. So something can be a function and not a one-to-one function. So here for each x, there's one y, but also for each y, there's one x. So our definition here is that each x value corresponds to only, and let me highlight that, only one y value. So that's always been the case with functions. But now, and each y value corresponds to only one x value. Okay, so the takeaway here is that for each x, there's one y, and for each y, there's one x. Again, if we go back to this example here, this is a function, but it's not a one-to-one function because this y value of 2 is associated with an x value of 2 and then also an x value of 3. So how can we determine if we have a one-to-one function? Well, previously we learned that we could use a vertical line test to determine if a relation was a function, right? This is a graphical test. So you have to first graph your relation and then draw vertical lines. And if any vertical line impacts the graph in more than one location, it's not the graph of a function. So why does this work? Well, remember, a vertical line is something like x equals some real number. Let's just call it a. It could be x equals -2. It could be x equals 7. It could be x equals, again, any real number. It could be a trillion. What happens is, for any point in that line, x is always the same value. So if that line impacts the graph in more than one location, well, that given x value is now associated with more than one y value, so that breaks or violates the definition of a function, so you don't have a function. Now, similarly, we can use a horizontal line to test for a one-to-one function. So a horizontal line is y equals some real number. Let's just call it k. So y equals 7 or y equals negative 100. Any of those would work. It's y equals some real number. What we need to know is on that horizontal line, the y value is never going to change. So if it impacts the graph in more than one location, that tells us that that given y value is going to be associated with more than one x value, so it's not a one-to-one function. So let's just blow through some examples real quick. And again, in the next lesson, I'll show you an algebraic method to kind of do this if you don't feel like graphing stuff. So first we have f of x equals the quantity x minus 2 squared. So immediately you would see that this is going to fail the horizontal line test. I'm just going to draw one horizontal line, and I'm going to do y equals 4. So what you can see is that this horizontal line that I drew, again, this would be y is equal to 4, okay? And what happens is it impacts the graph here and also here. So this is where an x value is 4. So this would be 4, 4. And this is where the x value is 0. So this would be 0, 4. So let's write these over here. We don't need this anymore. So you'd have 0, 4, and you would have 4, 4. So again, think about this. You have a y value of 4 in each case, and it's associated with two different x values. It's associated with an x value of 4, and it's also associated with an x value of 0. Now, you can clearly see what's causing this. It's because of this exponent here that's a 2. It's an even exponent. So what happens is when you have a 2 squared, you get 4. And then also if you get a negative 2 squared, you get 4 as well. If I plugged in a 0 for x there, you say f of 0 is equal to 0 minus 2, that would be squared. This is going to be negative 2, and it's squared, which is 4. Then also, if I did f of 4, this is what? It's 4 minus 2, that quantity squared. 4 minus 2 is 2. 2 squared is 4. So either way I get 4, and it's because of, again, that squaring operation that takes a negative and makes it positive and takes a positive and keeps it positive. So that's why for that given y value, you've got two different x values that's kind of associated with it. All right, let's look at one that is a one-to-one function. So we have f of x equals the square root of x plus 1, and then you have plus 4, and this is outside of the square root symbol, okay? So what we have here is a one-to-one function. You can draw as many horizontal lines through this thing as you want. You're never going to impact the graph in more than one location. And I'll just draw 2 lines. So just 2 lines. You can draw as many as you want or as few as you want. You can really just observe this thing and see that no horizontal line is going to impact the graph in more than one location. So this is going to be a one-to-one function. All right, let's look at another one that's not a one-to-one function. And again, as soon as I pull the graphs up, you can immediately tell it's not. You can see that a horizontal line is going to impact the graph in more than one location there. So f of x equals the absolute value of x plus 1 plus 1. So it's the absolute value operation that's giving us the problem here, because again, that takes a negative and makes it positive. It takes a positive and keeps it positive. So let's just draw one horizontal line here. So again, what you can see here is that it impacts the graph there and there. So that's 3, 5, 3, 5. And it's also going to be negative 5, 5. So negative 5, 5. So let's just see this real quick. If I did f of 3 as an example, this would be the absolute value of 3 plus 1, and then plus 1. We know the absolute value of 3 plus 1 is 4, right? 3 plus 1 is 4. Absolute value of 4 is 4. So this would be 4 plus 1, which is 5. So that's simple enough. Then f of negative 5 is going to give me the same thing. It's the absolute value of negative 5 plus 1. We know negative 5 plus 1 is negative 4. The absolute value of negative 4 is 4. So it's 4 plus 1 again, which is 5. So it's that absolute value operation that's creating this kind of effect where this y value of 5 is associated with two different x values, in this case 3 and negative 5. In this lesson, we want to continue to talk about one-to-one functions. And what we're going to do here specifically is we're going to focus on an algebraic method that's going to allow us to determine if a function is a one-to-one function. All right, so in our last lesson, we talked about one-to-one functions, and we also talked about how to determine if a function was a one-to-one function using the horizontal line test. Now, a one-to-one function, just to kind of recap, is where each x value corresponds to only one y value, and then also each y value corresponds to only one x value. Now, the quick way to kind of recap that is to say for each x there's one y, and then also for each y there's one x. Remember, when we had a function that wasn't one-to-one, it was okay for two different x values to correspond to the same y value. That's okay, that doesn't break the definition of a function, but it does break the definition of a one-to-one function. So in the last lesson, we talked about this horizontal line test. Basically, with a horizontal line, the y value is always the same. So if that horizontal line representing that kind of single y value impacts the graph in more than one location, that function is not going to be a one-to-one function because that single y value is associated with more than one x value. Now, additionally, we have an algebraic method that we can use. In some cases, this is faster. In some cases, it gets a bit complex. So it just depends on the given scenario. But if you're in a pre-calculus course or a college algebra course, a lot of times they'll tell you that you need to show this algebraically, and they'll give you reasonable examples to work on. All right, so this is what we want to start with here. It's just basically breaking down the definition we just saw, but into a more kind of algebraic format. So f is said to be one-to-one if, and only if, f of x sub 1 is equal to f of x sub 2 implies that x sub 1 equals x sub 2. So what does this mean? If you read this in your textbook, you might get confused by it. The only thing you need to focus on is the fact that when we have f of x, it doesn't matter if this is f of x sub 1. F of x in general is what? It's just a replacement for our variable y that we're so used to, right? It's the output of a function. So f of x sub 1 is just the output when I plug in the x sub 1 for each occurrence of x in that function. It's the same thing for f of x sub 2. It's just the output, or again, the y value, when I plug in x sub 2 for each occurrence of x in the function. Now, if these two y values are equal or the same, well, if the function is one-to-one, that can only be true if the two x values are the same. So that's all this notation is really saying here. It's written in a format that is confusing, but once you kind of break it down, it's not so bad. So what I want to do now is just show you a method that relies on this kind of notation here. And basically, we'll just jump right into an example. What you want to do, if we have f of x equals negative 3x minus 1, you want to say, okay, if I had f of, you can use x sub 1. I'm going to use a and b here. So I'm going to say f of a, this is negative 3a minus 1. All I did here was I plugged in an a where there was an x here. Okay, that's all we've done. And we've seen this before in previous lessons. Now, what I also want to do is I want to look at f of b. So what would that be? So it would be negative 3b minus 1. Again, all I did was I plugged in a b where there was an x in that function. Okay, so far so good. So from our notation, let's just go back to it. Again, we have f of x sub 1 is equal to f of x sub 2 implies that x sub 1 equals x sub 2. Well, instead of using x sub 1 and x sub 2, we're using a and b, just to keep it simpler. And so what I want to do here is say, okay, if it's true that f of a is equal to f of b, okay, then it has to be the case that a is equal to b, okay? Otherwise, this function is not going to be one-to-one. So what we can do is we can set these two equal to each other. Remember, f of a is actually equal to this, and f of b is actually equal to this, okay? So what I'm going to do is I'm going to set these two equal to each other. So I'm going to say negative 3a minus 1 is equal to negative 3b minus 1. And if it's a one-to-one function, it should be true that a is equal to b always. So let's go through and kind of simplify. This is really simple. We're just going to, you could say you're solving for a, or you could say you're solving for b. I'm just going to go through and add 1 to both sides. And what I'm going to do here is I'm just going to cancel this. And that's going to give us what? Let me just kind of scroll down a little bit. That's going to give us negative 3a is equal to negative 3b. If I divide both sides by negative 3, what am I going to get? Well, we know that this is going to cancel with this, and this is going to cancel with this. So I get that a is equal to b. So we've proved that this function is one-to-one. Let me erase this real quick, and let me just drag this up here. And let me just go back up so we can recap this real quick. We said that, again, if f of a is equal to f of b, and this function is 1 to 1, then it has to be true that a equals b. Well, we have f of a defined as negative 3a minus 1. We have f of b defined as negative 3b minus 1. So if I set these two equal to each other, and I go through a process of either you could say I'm trying to solve for a or b, it doesn't really matter, I end up with this a equals b, so I know this function is 1 to 1. Now, if you want to look at a graph of this guy, again, I don't have to draw horizontal lines here. You can see that this graph here, there's no horizontal line that would impact it in more than one location. So we know that this function is going to be 1 to 1. When you first start doing this, if you want to kind of graph it to check and make sure that you got the right answer, that's probably a good idea. All right, let's look at another example. So we have f of x equals the absolute value of x plus 2. Again, if I use f of a, this is what? Just plug in an a where there's an x. That's all you have to do. So a plus 2. Then for f of b, okay, I'm just going to now plug in a b where there's an x. So we'd have b plus 2. Nothing that's too fancy, nothing that's too confusing. Again, if f of a is equal to f of b, then it's got to be true that a equals b. And that's got to be true all the time. So what can we do here? Again, this is f of a, this is f of b. So if these two are equal, set them equal to each other and let's see. So we have the absolute value of a plus 2 is equal to the absolute value of b plus 2. Now, we've solved absolute value equations before, and we know that if we have an absolute value expression equal to another absolute value expression, well, these two can only be equal if what? The first scenario is you drop the absolute value bars. So the first scenario would just be a plus 2 is equal to b plus 2. But because you have absolute value involved here, there's going to be an or, right? So it could also be true that the negative of one of these expressions is equal to one of the expressions. So in other words, I would drop the absolute value bars. So I'd put a plus 2 is equal to b plus 2. And then I would wrap one of these in parentheses. It doesn't matter which one. And I would put a negative sign out in front. Now, you can distribute that and say this is negative a minus 2. And what's going to happen is you're going to run into a problem, okay? So over here, it's fine. I subtract 2 away from each side, and I get a is equal to b. But this is where it gets messed up because you have this or. And over here, I have negative a minus 2 equals b plus 2. Let's just solve it for a. So in that particular case, I would add 2 to both sides, and I would have negative a is equal to, this cancels, b plus 4. And then to get a by itself, let's divide both sides by negative 1, or you could multiply by negative 1, it doesn't matter. So let's divide both sides by negative 1. And let me scroll down and get a little bit more room. So we know that this is going to cancel, and I'll have a is equal to negative b minus 4. Now, the problem lies in this one right here, okay? It's okay, this one right here on the left is fine, but you have this or situation, and that's what throws a wrench in this, so this function is not going to be 1 to 1. So let's look at this graphically, and we can clearly see this function is not 1 to 1. If I drew a horizontal line through, if I go up to y equals 4, so let's say I had a horizontal line, y equals 4. Let's just draw that in real quick. And not perfectly straight, but you get the idea. And when I look at this guy, again, it's going to impact the graph here and also here. So that's an x value of 2 and a y value of 4. So 2 comma 4 works. And then also an x value of negative 6 and a y value of 4. So an x value of negative 6 and a y value of 4. So this y value of 4 is associated with two different x values, 2 and negative 6. So of course, this is not a 1 to 1 function. All right, let's take a look at another one. So now we have f of x equals, we have 1 over x minus 2, and then plus 2. So again, I'm going to go f of a is equal to 1 over a minus 2, then plus 2. And then I'm going to do f of b is equal to 1 over b minus 2, and then plus 2. Okay, so again, what I want to do is set these two equal to each other. So this is f of a, this is f of b. Set them equal to each other and show that a equals b if this guy is 1 to 1. So 1 over a minus 2 plus 2 is equal to 1 over b minus 2 plus 2. Well, I have 2 on each side, so I can just get rid of that, right? If I subtract 2 away from this side and I subtract 2 away from that side, I'm just subtracting the same thing away from both sides of the equation. So it's going to cancel over here and cancel over here. So let's scroll down now. And what we have is 1 over a minus 2 is equal to 1 over b minus 2. So the quickest way to solve this is just to cross multiply, okay? So what we would have is what? We would have b minus 2 times 1, which is just b minus 2, is equal to a minus 2 times 1, which is just a minus 2. And of course, now I can just add 2 to both sides of the equation. This is gone, this is gone. And what I get is that b is equal to a, or you could say a equals b, it doesn't really matter, but you've proved that this is a one-to-one function. So here's the graph, and this one is a bit confusing because you do have that horizontal asymptote at y equals 2. But all we're doing here is this graph, if I'm going to the left, it's approaching a y value of 2, but it's never going to actually touch it. This guy is constantly getting closer and closer to 2, but the value isn't always the same, right? It's getting closer and closer. It looks like it graphically because it gets infinitely close to 2. In our eyes, when we look at that, we say, oh, that looks like a horizontal line would hit that in more than one location, but it wouldn't, right? So you just have to understand the fact that this is an asymptote, and the idea is that it's getting closer and closer and closer. It's not going to actually touch it, but the values aren't the same, right? So those y values are changing. All right, let's look at another one. So now we have f of x equals the quantity x minus 3 cubed plus 1. So we already know what to do. So we're going to go f of a is equal to the quantity a minus 3 cubed plus 1, and then f of b is equal to the quantity b minus 3 cubed plus 1. Okay, so we're going to set these two equal to each other. So I'm going to say the quantity a minus 3 cubed plus 1 is equal to the quantity b minus 3 cubed plus 1. So we know that we have 1 on this side and 1 on this side, so I can subtract 1 away from both sides, and that's going to go away in each case. So now what I'm looking at is a minus 3 cubed is equal to b minus 3 cubed, okay? And what I can do to get rid of this kind of exponent of 3, I can use kind of the inverse operation. I can take the cube root of both sides of the equation, or I could really raise both sides to the 1/3 power. It doesn't really matter how you think about that. I'm just going to say I'm going to take the cube root of both sides of the equation. And so we know that this index is going to cancel with this exponent in each case. And that's going to leave me with just this part right here. Okay, so I'm going to have that a minus 3 is equal to b minus 3. And let's scroll down a little bit. And we can add 3 to both sides of the equation. And we will have that a is equal to b. So a is equal to b here. So graphically, when we look at this guy, we can see that no horizontal line would impact this in more than one location. You can see this kind of spot here looks like it might, but it's not. This guy is constantly changing in terms of the y value. So this is going to be a one-to-one function. In this lesson, we want to talk about how to find the inverse of a function. Over the course of the last 2 lessons, we talked about how to determine if a function was a one-to-one function, meaning for each x it had one y, and also for each y it had one x. So once we understand that concept, if we have a one-to-one function, we can then find something known as the inverse of that function. And when we talk about a function and its inverse, they basically reverse each other. So the x and the y values are going to be swapped. So to see that with a very simple example, let's start out with f. And f is just a very simple relation, and it's also a function, and it's also a one-to-one function. So it just contains 3 ordered pairs. So 3, 2, -1, 7, and 5, 1. If we say that g is going to be the inverse of f, then all we need to do to find this is just swap the x and y values. So this ordered pair, again, this is x, y. This ordered pair is 3, 2. So down here, when I form this ordered pair, I just swap them. So the 2, that's the y value, will become the x value. And the 3, that's the x value, will become the y value. Now, moving on to this one, I'm going to do the same thing. And I can just kind of draw this like this. I'm just going to swap. So this will become 7, and this will become -1. So a y value of 7 became the x value of 7 in the inverse. And then the x value of -1 became a y value of -1 in the inverse. And again, we're just going to do the same thing one more time. So this will be a 1 and this will be a 5. So we're just swapping the x and y values. It's a pretty simple thing overall. The next thing you're going to come across in this section is they're going to ask you to find the inverse of a one-to-one function. So we already know something like f of x equals 3x plus 5 is a one-to-one function. Again, we know how to prove that graphically and also algebraically. So once you've determined that it's a one-to-one function, how can you find the inverse? Well, basically what you want to do is replace f of x with y. So you're going to go y equals 3x plus 5. So that's the very first step. Then the next thing you want to do is you want to swap x and y. Remember, these guys are going to be reversed. The x values become y values and the y values become x values. So if I swap x and y, you can kind of do it like this. I'm going to say this is x and this is y. And now what I'm going to do is I'm just going to solve it for y. So I can just erase this so I have enough room to do this. Let me just kind of slide this up. And to solve it for y is very easy. We subtract 5 away from each side of the equation. We know that this is going to cancel, and I'll have x minus 5 is equal to 3y. And let me erase this because I like my y on the left. So I'm going to put 3y is equal to, we have x minus 5. I'll erase this now. So how can I solve for y? We have this 3 that's multiplying y, divide both sides by 3. And of course we get that y is equal to x minus 5 over 3. So this guy and this guy are inverses. The notation seems a bit different because we have f of x and then y. So to fix that, I'm going to change this, and I'm going to put some special notation in here. I'm going to say f inverse of x. Okay, so that's how that's read. It's not f to the power of -1 as it appears to be. So if we think about this, the common mistake is you see this notation and you're thinking about exponents and you're saying, okay, f inverse of x is 1 over f of x. No, no, no. This is completely wrong, okay? So this is just the way that we notate the inverse, okay? So it's not 1 over f of x. Now, let's think about this for a moment and see how these guys reverse each other. If I think about what f of x does, if I plug something in here for x, well, what happens to it? We multiply by 3. So step 1 is we multiply by 3. And then what do we do in step 2? We add 5. So then we add 5. Okay, so that's the first one. What happens in the inverse? Well, the first thing is when you plug something in for x, what happens? The first thing is I subtract 5. I subtract 5, okay, away from whatever x is. So you see how this is going to reverse what this is. If I add 5 to something and then I subtract 5 away from something, I'm basically reversing that and getting back to where I started. If I started with 3 and I added 5 and then I subtracted 5, well, I'm back to 3, okay? So if I look at this here, the second step is what? It's going to reverse this multiplication by 3. And we see that once we've subtracted away 5, we divide by 3 down there. So we can put divide by 3. So what this is telling me is that when I plug something in for x and I go through the multiply by 3 step and the add 5 step, if I take that result and then plug it back in here, it's going to completely undo what I've done. It's going to first subtract away 5, okay, undoing this, and then it's going to divide by 3, undoing this, and I'm going to get back what I started. To show you this, let's just erase this so we have enough room. Let's just pick one number, and we could just choose something easy like 2. So f of 2 would be what? So I'm just plugging in a 2 for x here. And that would be 3 times 2 plus 5. Again, the first thing is I'm multiplying by 3. 3 times 2 is 6. Then I add 5 to the result. 6 plus 5 is 11. Okay, so if I take this result and I run it back through the inverse as the input, I'm going to go back to 2. Okay, that's all it's saying. So then f inverse of 11 should be equal to 2. So what would we have? We would have 11 minus 5 over 3. Again, the first thing I'm doing is I'm subtracting away 5. I'm undoing this part right here. 11 minus 5 is 6. So now I'm back to that. And then the next thing I'm doing is I'm dividing by 3. Okay, so I'm undoing this part right here. 6 divided by 3 is 2. So what you see is that in the first one, we have an ordered pair that's 2, 11. In the second one, we've reversed that ordered pair. If I plug in 11, I get back to 2. So these guys, again, they reverse each other. So this is the main concept of an inverse. All right, let's take a look at another example. Again, when you get these problems, they're very simple. You just want to start out with taking this f of x and making it y. And then you're just going to swap x and y. So we can just erase it if you want and say this is y and this is x, and then just solve for y. Okay, so pretty easy. So we're going to add 2 to both sides, and I'll just do this over here. We're going to have x plus 2 is equal to 2y cubed. Now let me erase this, and I'm going to flip the order because I like y on the left. So 2y cubed is equal to x plus 2. And then from here, how can we solve for y? Well, we have 2 steps we have to do. We first are going to divide both sides by 2. And that's just going to clear this out, so I can just erase it. And then the last thing is, this is raised to the 3rd power. I can undo this by taking both sides to the kind of 1/3 power, or we could say we take the cube root of each side. Either way you want to show that, okay? And I didn't make that kind of long enough, so let me redo that. So what's going to happen is this will cancel, and I can really make this a lot better. So let me kind of slide this down so we have some room. And I'll do that properly. So y is equal to the cube root of x plus 2 over 2. And really, you just change this at this point. Say this is f inverse of x, and you're done, right? You found your inverse. So these guys are inverses. Again, you can pick a number, plug it in, and run it through here. And then what happens is, let's just do one for example. If I do 2, well, 2 cubed is 8. 8 times 2 is 16. 16 minus 2 is 14. So this would be 2 and 14. If I take 14 and plug it in here, I'm going to get a 2. Okay, so 14 plus 2 is 16. 16 divided by 2 is 8. The cube root of 8 is 2. So again, you get 14 comma 2 as an ordered pair here. So again, these guys are just reversing each other. The x and the y's are just going to be swapped. Let's take a look at one that's a little bit harder to wrap things up. So we have f of x equals, we have x minus 5 over 2x plus 3. So in this case, you have 2 x's in your problem. So you're still going to do the same thing. So I'm still going to change this one into a y and this one into a y. So I'll say y is equal to x minus 5 over 2x plus 3. Again, just swap these. So I'm just going to, and let me kind of do this down here. We're going to need a lot of space for this. I don't want to erase anything because people get confused on this one. So I'm going to be switching this and this into a y. And this one, I'm going to change into an x, okay? So we'll have x is equal to y minus 5 over 2y plus 3. So far, not too bad. Now, let me scroll down and get lots of room. You want to solve this guy for y, but you have 2 y's involved. So what you're going to have to do is you're going to have to get all the y's to one side, okay? You're going to have 2 terms that are not going to be like terms with y's in it, and then you have to factor the y out. Okay, we've already done this earlier in the course, but it's been a while, so you probably have forgotten. So what I'm going to do, let me just slide this down a little bit. I'm going to multiply this by this denominator, so 2y plus 3. And I'm going to multiply by the denominator over here. So it's going to cancel from here. And what I'm going to have is this 2y plus 3 times x, which is basically x times 2y. So let's put 2xy. And then plus x times 3 is 3x. And this equals my y minus 5. So I've got a y here, and I've got a y here. So I've got to get all those terms to the left. Everything else is going to go to the right. So let me subtract 3x away from each side. And let me subtract y away from each side. And what is that going to give me? Well, we know that this cancels and this cancels. So don't worry about that. We're going to have 2xy minus y is equal to negative 3x minus 5. Okay, so now what I want to do, I want to factor this y out, okay? So if I do that, I'll have y, and then inside of parentheses, I'll have 2x minus 1, and this equals, we have this negative 3x minus 5. So I'm going to run out of room here, so let me copy this, and I'm going to start a new sheet, and we'll just paste this in so we can keep going. So now all I need to do, think about this, y is being multiplied by this right here. Okay, I know this doesn't look like if we had something like 6y equals 30 and we divide both sides by 6 to say y equals 5. It's the same thing here. Y is being multiplied by this quantity 2x minus 1. So to get y by itself, I just divide both sides by that quantity. And this cancels. And so I find that y is equal to negative 3x minus 5 over 2x minus 1. And let's just paste this in here. And I'm going to erase the y, and I'm going to put f inverse of x. So we have our correct notation. And again, you can choose some point arbitrarily and show that it reverses itself. In the next lesson, I'll show you how to prove that you have inverses, but for now, we'll just show this with a simple point. So let's just go with an x value of 1 again. So f of 1 is 1. Plug in a 1 here. 1 minus 5 is going to be negative 4. And this will be over. 2 times 1 is 2, plus 3 is 5. So you get negative 4/5. So the ordered pair here would be 1, comma, negative 4/5. Now, if I take this negative 4/5 and plug it in for x, I should get 1 back. So I should get the ordered pair negative 4/5, comma, 1. So let's try that. So if we had f inverse of negative 4/5, this would be negative 3 times negative 4/5 minus 5 over 2 times negative 4/5 minus 1. So let's do this in the numerator first. So we know that nothing's going to cancel here. You would have negative 3 times negative 4, which is positive 12. So you'd have 12/5, then minus 5. You can multiply this by 5 over 5. And basically what you'd have here is 25. So 12 minus 25 is negative 13. So this would be negative 13/5. Then down here, 2 times negative 4/5 would be negative 8/5. So this is negative 8/5. And then you're subtracting away 1, so you can say minus 5 over 5. Now negative 8 minus 5 is negative 13. So this would be negative 13/5. So what do we get? Negative 13/5 divided by negative 13/5. The same non-zero number divided by itself is 1. We know that this would be negative 13/5 times the reciprocal of this, which is 5 over 13, and it's negative. And again, these cancel and become 1, which is exactly what we said, right? We plugged this in, we got a 1. So these guys are inverses of each other. Again, in the next lesson, I'll show you exactly the process you can use to prove this. In this lesson, we want to talk about how to determine if two functions are inverses. So in the last lesson, we learned how to find the inverse of a one-to-one function. Basically, we swap the x and y values, okay, and then we just solve for y. And then we use our special notation f inverse of x. That's all there is to it, really. So in this kind of section here, what I want to do is show you how to determine if two functions are inverses. So they give you two functions, one f, one g in most cases, and they say, hey, determine if these two are inverses. So the rule for this is very, very simple. If they're inverses, then f of g of x is equal to x. So this is f composed with g. We already saw this earlier in the course. And then also, we'll say and here, g of f of x is equal to x as well. So both of these conditions have to be met. Don't just check one, you have to check both. So if we have f of g of x, so f of g of x, what is this equal to? Well, again, we already know how to do this. We take f of x, which is 2x minus 9, and everywhere there's an x, there's one right there, we're going to plug in g of x. So g of x is this guy right here. So what I'm going to do is I'm going to plug this in for x there. I'm just going to simplify. So I would have 2, this guy right here, times x, plug this in for x, so times x plus 9, over 2, and then I'm subtracting away 9. So what does this give me? Let me scroll down. Well, we know that 2 over 2 is 1, so that's gone. And we basically have what? You'd have this numerator here of x plus 9, and then minus 9. And this equals what? 9 minus 9 is 0, so this is just x. So in the first case, it's true, right? We have f of g of x is x. So let me erase everything, and let's just put a check mark here. And now let's do g of f of x. So g of f of x. And what's this going to be equal to? We'll take g of x, and everywhere there's an x, there's just one. We're going to plug in f of x. So again, this gets plugged in right there. That's all we're doing. So you'd have 2x minus 9, okay, that's for x there, then plus 9. Then over, your denominator is going to be 2. So let me scroll down, so we have some room to work. And what do we have first? We have minus 9 plus 9, so you can basically say this is plus negative 9. So negative 9 plus 9 is 0. You can basically cancel those out and say this is 2x over 2, which is just x, right? This cancels. So we've proved the other condition, and let me erase this also. And I'll just put another check mark here. So f of g of x is equal to x, and g of f of x is equal to x. So if both of those are true, they're inverses. So if you wanted to, you could really kind of scratch this out and say this is f inverse of x like this. If you wanted to, I'm just going to leave it as g of x for now. But you might also see this notation as f of f inverse of x. So in some textbooks, they'll do that and say this has to be equal to x. And then also the and, okay, the and here would be f inverse of f of x would be equal to x. So again, both of these have to be true. So you might see it this way or the other way. All right, so let's erase this and let me show you why this kind of works out. To get a good intuition into this, because this is generic notation, let's just pick a point that works here. So let's just say f of 2. F of 2 is equal to what? You'd have 2 times 2, which is 4, minus 9, which is negative 5. So an ordered pair here that works is 2 comma negative 5. So 2 comma negative 5. Again, with the inverse, those are going to be flipped. So the y value becomes the x value becomes the y value. So it should be true that an ordered pair that satisfies g of x would be negative 5 comma 2. Well, let's see if that's the case. So g of negative 5 is equal to what? Well, you'd plug in a negative 5 here and then plus 9, that's 4. 4 divided by 2 is 2. So these two are kind of the reverse of each other. The x value became the y value and the y value became the x value. Now, let's think about this a little bit more deeply. If I think about, let's just take the first scenario, f of g of negative 5, okay? What is g of negative 5? G of negative 5 is the y value that you get when you plug in a negative 5 in for x in g of x, okay? So we already know that if I plug in a negative 5 here, I get a 2, okay? So what's going to happen is what? This turns out to be f of 2, because this right here, g of negative 5, we already know that's a 2. So now I have f of 2, and I want to say, what is f of 2? Well, I go back up here, I know this is negative 5. So f of g of negative 5, I can just erase this, is negative 5. Okay, and you can play around with this a little bit more, but basically that's all we're saying. F of g of x is equal to x for any x in that domain. And then g of f of x is equal to x, again, for any x in the domain. So again, just play around with this for a little while, and this will start to make some sense for you. Again, when you work with generic notation, a lot of times it's confusing. Okay, let's go ahead and jump in and look at another one. So we have f of x equals the cube root of x minus 3, and g of x equals the quantity x plus 3 cubed. So are they inverses? So let's check f of g of x first and see what we get. So this is my f of x. I'm going to plug this in here for x. So again, this whole thing gets plugged in there. So you would have the cube root of the quantity x plus 3 cubed, and then you'd be subtracting away 3 out here. So what does this give me? Let me scroll down and get some room. We know that this kind of index would cancel with this exponent here, and I'd just be left with this x plus 3. So I would have x plus 3 minus 3, which is just equal to x. So the first condition is true, f of g of x is x. So what about g of f of x? So g of f of x is equal to what? So let's scroll back up. And again, I'm starting with g of x, and I'm just going to plug in for x there, and this is what I'm going to plug in. So I would have inside the parentheses this cube root of x minus 3, and then you'd have plus 3, and the whole thing is cubed, okay? So what do we have here? Well, we have this minus 3 plus 3. That can be done. So minus 3 plus 3 is obviously 0. So I can say this is the cube root of x, and then this is cubed. Again, this is going to cancel with this, and I'm just left with x. So in both cases, the f of g of x is x, and g of f of x is x. So because both of those conditions were met, we can say these guys are inverses. All right, let's take a look at another one. So now we have f of x equals, we have 2 over x minus 1 and then minus 3. And we have g of x equals, we have negative 3 over x minus 1 and then minus 2. So again, I'm just going to start with f of g of x. Okay, this equals what? Well, I'll have 2 over, where I have an x here, I got to plug this whole thing in. So be really careful with this. So I'm going to do negative 3 over x minus 1 and then minus 2. So this whole thing right here got plugged in right there. Okay, you see that. So if I just kind of x this out now, what's left? Well, I have minus 1. Okay, that's got to be done. And again, that's in the denominator down here. And then outside of this, I've got minus 3. So this one's really, really easy to make a mistake on. So be very, very careful when you're plugging stuff in. So let's scroll down so we have a lot of room to work. So the first thing I'm going to do is do -2 minus 1. And I'm just going to do that in line and say this is -3. And now I would need a common denominator here. So I would multiply this. And before I do this, let me put plus -3 so I don't make a silly sign mistake. So I'm going to multiply this by the quantity x minus 1. And this is all kind of running over the quantity x minus 1. Okay. So let me fix this real quick so it doesn't run over here and get confusing. This is going to be -3x plus 3. So -3x plus 3. And you're going to have a common denominator, so you can just get rid of this, and you can just kind of extend this over. We'll say this is x minus 1 here. Now, before we deal with anything over here, realize that you have a complex fraction here. So really what I can say is that I have 2 over 1 divided by, and if I simplify this, -3 plus 3, those are going to cancel, okay? So what I'd have is 2 over 1 divided by -3x over x minus 1. So this equals what? 2 over 1 times the reciprocal of this, which is x minus 1 over -3x. Okay, so now that we know that, let's go ahead and multiply 2 times x, that's 2x. And then 2 times -1 is -2, and this is over -3x. So this is over -3x. Now, I have this -3 over here that I have to deal with. I want to get a common denominator going. So what I'm going to do is I'm going to multiply this by -3x over -3x. And again, to not make a sign mistake, I'm going to put plus negative here. Really easy to make a sign mistake and blow the whole thing. So I'm going to say that this is equal to 2x minus 2. And then you have -3 times -3 times x. So this will be plus 9x. And then this is all over the common denominator of -3x. So what does this give me? 2x plus 9x is 11x. And then you have -2. And this is over -3x. So obviously this is not equal to x. So you can say these two are not inverses of each other. You don't have to go back and check g of f of x. If one of them fails, they're not inverses. In this lesson, we want to talk about how to find the inverse of a function with a restricted domain. So in a lot of cases, you're going to come across a one-to-one function that has an inverse, but that also has a domain restriction involved. So a lot of these that you're going to see in your book are going to involve kind of square roots. So something like f of x equals the square root of x plus 1. So we're going to see this as a one-to-one function, and it does have an inverse, but we have to be really careful when we calculate it, okay? So let me explain why. First and foremost, we know this has a domain restriction because when we work with the set of real numbers, we cannot take the square root of a negative. Unless somebody specifically tells you otherwise, you're working with the set of real numbers. So we have the square root of x plus 1. We know that this part right here cannot be less than 0. So x plus 1 has to be greater than or equal to 0. It can be 0, that's fine. Square root of 0 is 0, you're okay. But it can't be negative. You get square root of -1, you get into complex numbers, or you say there's no real solution. All right, so from here, I can solve this by just subtracting 1 away from each side, cancel that out, and say x is greater than or equal to -1. So let's just list this here and just say that this is valid for x that is greater than or equal to -1. Okay, now if we look at this graphically, we can clearly see that this guy is a one-to-one function, right? It passes the horizontal line test with flying colors. But we can also see that our domain restriction is here, right? You can see this point right there, which is the point -1, 0, okay? That's the leftmost point on this graph. So for any x value to the left of that, it doesn't exist on this graph. It's going to be either -1 for the x value or anything to the right or anything larger going out to positive infinity. Now let's think about if we found the inverse of this guy without considering the domain restriction. What's going to happen? So let's go ahead and say this is y equals the square root of x plus 1. Let's swap x and y. So I'm going to swap this and I'm going to swap this. So I'm going to say this is x equals the square root of y plus 1. And then to get rid of this kind of radical here, I'm just going to square both sides. So I'm going to have that x squared is equal to, this will cancel with this, and I'll have this y plus 1 here, so just y plus 1. Because I want my y, what I'm solving for on the left, that's just how I like it, I'm just going to go ahead and flip this guy. It's completely legal. So I'm going to say y plus 1 is equal to x squared. And then to solve for y, all I need to do is subtract, and I meant to use a marker there, subtract 1 away from each side of the equation. This will cancel, of course, and you get y is equal to x squared minus 1. Now, in most cases, we would stop and say this is the inverse, right? So we would erase this and say f, and let me kind of slide this down because I'm going to run out of room. So we'll say f inverse of x is equal to x squared minus 1. But then you'd scratch your head and say, I don't think that's true because this, if I had g of x equals x squared minus 1, that's not a one-to-one function. So what's going on? So let's take a look at that graphically. This is, let's just say g of x equals x squared minus 1, right? So if I had g of x equals x squared, and then I shifted it down 1 unit, that's this graph here. So this thing would fail the horizontal line test like crazy, right? You can make a bunch of different horizontal lines that would fail all over the place. So what do we need to do to fix this? Well, we need to impose a domain restriction. So let's go down here and consider these two graphs side by side. I want to think about the domain of this one, and then what should be the domain of this one, okay? If we consider that this guy is going to end up being the inverse. Well, let me kind of go down and isolate this one for a moment, and we can think about this further. When we find the inverse of a function, we swap the x and y values. So what that tells me is that the domain, okay, from the first one, let's just say f of x, becomes the range in the inverse, f inverse of x. So if I consider my f of x function, and I just think about my domain, well, we already know that it's the set of all x such that x is greater than or equal to -1. We found that earlier. But what about my range? We can look at the graph and see this, or you can go back and play around with the equation, but you can easily see from the graph that the lowest point is again here, which is at -1, 0. Every other point on that graph is going up, and it's going to go out to positive infinity. So the range we could say is the set of all y. Let me make that a little better. So we'll say the set of all y such that y is greater than or equal to 0, right? It can be 0 or anything larger. Now, because the x and the y's get swapped when we think about the inverse, so let me do this in a different color. If I do f inverse of x, well, now what's going to happen is the domain takes on the range. So it would be the set of all x such that x is greater than or equal to 0, and the range would take on the domain. So it would be the set of all y such that y is greater than or equal to -1. And if we want to see this graphically, I've already plotted the function f of x, which is in blue. So this is f of x. And I've plotted the inverse, which is this guy in, I guess that's orange. I'm not really sure. So f inverse of x is right there. And you can see that we've kind of cut the left side of the parabola off. We got rid of it completely. We only considered x values that were greater than or equal to 0. So this is kind of the start of this thing when you consider the x values. It's the x value of 0. And then it continues out to positive infinity. And a couple of things you can notice about the graph and its inverse. The first thing is, if you graph the line y equals x, which is this guy in red, maybe pink, not sure. So let's say y equals x, but it's this line right here. What happens is when you have a graph and its inverse, you can take a given point and reflect it across this line y equals x, and you'll come over here. So this point right here is 8, 3. So this is 8, 3. If I fold it across the line y equals x, I'll come over here to 3, 8. So again, you can see that the x and the y values just swapped. Okay, that's all you're really doing. And you can take other points. If I took this one right here, this is 3, 2, fold it across the line, I get to 2, 3. Okay, so on and so forth. You can take this point, fold it across the line, get to there. This point, fold it across the line, get to there. Again, so on and so forth. So if we go back to right here where we wrote this, we need to put a domain restriction in for this to be valid. We can't say that this is true right now. Okay, so let's copy this and slide it over here. And we're just going to put a comma here and say that x needs to be greater than or equal to 0. And for this one, x needs to be greater than or equal to -1. So this is how you would want to list this. This function does have an inverse. It's this, but with a restricted domain. Now, I want to prove this to you even further. Let's go down to a fresh sheet. And let's just write f of x is equal to the square root of x plus 1. And I'm going to write the other one as just g of x, just so I can save a little bit of that notation that makes everyone crazy. So I'm going to say this is x squared minus 1, okay? So if I don't consider any domain restrictions, what happens is when you do the check, remember you have this f of g of x is equal to x, and remember that g of f of x is equal to x as well. One of them is going to fail. And it's going to fail, and to a lot of people, because they don't remember the kind of rules that we talked about with basic algebra, they're going to think it didn't fail. So let me show you this real quick so that you understand what's going on. So let's say I try f of g of x. So f of g of x, so I would take this function here, f of g of x, and I would plug in, right there, I'm plugging this in. Okay, so I would take square root of, this is going to be x squared minus 1, and then plus 1. Okay, so far everything looks fine and dandy. I know that minus 1 plus 1, that's going to go away. So I have square root of x squared. And a lot of people at this point go, oh, that worked. So this cancels with this and it equals x. It doesn't though. So if you remember back, let me kind of erase this, from kind of the basic stuff we did at the very beginning of the course, we know that the square root of x squared is equal to the absolute value of x. To prove this real quick, let me scroll down. I'll come back up. Let's say I took the square root of something like negative 4 squared. Okay, I have a negative 4. So this is not going to be equal to negative 4. It's going to be equal to positive 4. Why? Because negative 4 squared is done first. So negative 4 squared, that quantity is 16. So let me just erase this and say, now you have the square root of 16, which equals positive 4. So this became positive. So you have to be careful about this, okay? So it would only be true, let me kind of erase this real quick. It would only be true that if x was greater than 0 or equal to 0, that the square root of x squared would be equal to x. Because the absolute value of x is equal to x if x is greater than or equal to 0. And then the absolute value of x is equal to the negative of x if x is less than 0, okay? But because we put a domain restriction in here, we can throw this case out, and we could say that, okay, the absolute value of x just equals x because we have x restricted to be greater than or equal to 0. So then we can say that this is actually equal to x because we're following this domain restriction. So that's how we make this work out. Again, if you're not paying attention and you forget that the square root of x squared is equal to the absolute value of x, you'll mistakenly just cross those out and say this is x, it works out, what's this guy talking about, okay? So you have to be very, very careful about this. So we're going to come back up here and we're going to make sure that when we list this, we again, let me kind of slide this down, put our domain restriction in and say x needs to be greater than or equal to 0 for this to be true. Okay, it's true only when that happens. Now, if we erase this and do the other one, there's no issue, no problem. So we're going to say g of f of x is going to be equal to, so instead of x squared, remember I'm plugging this in for x, so I'm going to have the square root of x plus 1. This quantity would be squared and then minus 1. No issues here. You can go through and just cancel this away and say this is what? It's x plus 1 minus 1, which equals x, okay? So that's why it's very important to check both of these, okay? That's why we told you that earlier, where a lot of people just want to check one and be done. If you get something like this and you just kind of fly through it and you're not paying attention, you're going to get the wrong answer. And especially on something like the SATs or the ACTs, they know these are common things that you'll make a mistake on, and they're good trap questions. Let's take a look at one more. So suppose we have f of x equals 1 over the square root of x. So we already know that this guy would have a domain restriction, right? We would say that first and foremost, you can't take the square root of a negative, okay? So we know that x would need to be greater than or equal to 0. And then also, it's in the denominator, so x can't be 0, so you can just erase that. So that's my domain restriction. What's my range here? Okay, because I got to think about that. When I do the inverse, I've got to know what the range is because that's going to be my domain in the inverse. I know that I can't plug in a 0 there, but if I plug in something that is between 0 and 1, okay, something in that range. So let's say x was greater than 0 and less than 1, what's going to happen? Well, the closer I get to 0, remember, this is going to become a really, really, really small number. Infinitely small if you want it to be. And 1 divided by some infinitely small number is going to approach infinity. So if x is greater than 0 and less than 1, we know that the y value is approaching positive infinity, okay, as we get closer and closer to 0. Now, if x is 1, we know y is just 1. And then if x is some larger number, let's say you start getting something like, I don't know, let's say you plug in 4. Okay, well, square root of 4 is 2, you get 1/2. And then as you increase this, it approaches a y value of 0. But it's never going to actually touch it. So the range here would be the set of all y such that y is greater than 0. So the domain and the range are actually the same. Okay, so the domain is the set of all x such that x is greater than 0. The range is the set of all y such that y is greater than 0. So when I find the inverse, this range here will be the domain. So let's go to a fresh sheet, and we'll say that f of x is equal to 1 over the square root of x. And I'll just go ahead and say that we'll have y is equal to 1 over the square root of x. I'll interchange or swap x and y. So let me do that over here. I'll say now that we have x is equal to 1 over square root of y. And what I can do now is square both sides. But actually what I'm going to do is I'm just going to take this guy. We know that y right now is raised to the 1/2 power. So I can just say this is raised to the 1/2 power. And if I wanted to drag it into the numerator, I could say it was y raised to the power of negative 1/2. Well, how could I cancel that? Well, I could raise both sides to the power of negative 2. So let me raise this side to the power of negative 2 and this side to the power of negative 2. And so I get x to the power of negative 2, which is 1 over x squared, is equal to y, right? Because power to power rule, those guys are going to cancel and become 1. Now, let me erase this over here. And erase this. And let's state this as our inverse. We'll say f inverse of x is equal to, we'll have 1 over x squared. But again, we have to put our domain restriction in here. So we say that x needs to be greater than 0. And again, my f of x is equal to 1 over the square root of x. And we'll say again for the domain here, x is also greater than 0. Now I'll leave it up to you to prove this. You can go back and do the f of g of x, or in this case, because we have this notation, you can say f of f inverse of x is x, and then f inverse of f of x is also x. And you need to do this with the domain restriction. If you don't, in one of the cases, you're going to run into that problem where you have the square root of x squared, and that becomes the absolute value of x. So you're going to have to restrict that domain to kind of clear that up. In this lesson, we want to talk about graphing exponential functions. So most of you have worked with exponential functions before. They're of the form f of x equals a, which is our base, raised to the power of x, which is our exponent. So notice that you have a variable now in the exponent. And basically, you need to pay attention to these two restrictions on the base. We say here that a, again, the base is strictly greater than 0, and also a, the base, is not allowed to be equal to 1. I'll talk more about those restrictions in a moment. For right now, I want to talk about the kind of general expectations of what you're going to see when you graph one of these guys. First and foremost, it's not that easy to do because of the kind of limitations of a hand-drawn graph. If you have a smaller base, like 2 or 3 or even 4, it's doable. But when you get into higher bases, let's say use 12 or something like that, well, you're going to have a problem kind of doing this by hand, because if I had something like f of x equals 12 to the power of x, well, 12 to the first power is 12, but then 12 squared is already 144. Okay, so can you plot 2, 144 with a sheet of graph paper? It's going to be really hard to do. So that's why these are pretty difficult to graph overall, and your textbook is usually going to use these kind of smaller bases, as I am going to do as well today. So on your graph, as long as your base a is greater than 0 and not equal to 1, you're going to have these 3 points. So negative 1, 1 over a will be 1 point, 0, 1 will be another, and 1, a will be another. So you can use these 3 points to kind of get things started and then find additional points as needed in order to sketch your graph. Let's say you had something like f of x is equal to, let's just use 2 to the power of x, very common example. Well, if I plugged in a negative 1 for x, f of negative 1 here would be 2 to the power of negative 1, which is 1 over 2 to the power of 1, which is just 1 over 2. Okay, and this is always going to be true, again, as long as a is greater than 0 and not equal to 1. If I had something like g of x is equal to, let's say, 5 to the power of x, Well, if I had g of -1, well, this is what? It's 5 to the power of -1. This is just 1 over 5 to the power of 1, which is just 1 over 5. So it's always going to be 1 over whatever the base is. Okay, in this case, it's 5, so we get 1 over 5. In this case, it was 2, so we got 1 over 2. All right, so we understand that one. So let's go to the next one. And the next two are very easy to understand. So you have 0, 1 as a point. Again, if you raise something to the power of 0, as long as it's not 0 itself, you get 1. And we know that we're not going to deal with 0 because this base here is restricted. It can't be 1, and it can't be something that's 0 or less. So we're good to go. If I raise 2 to the power of 0, I get 1. If I raise 5 to the power of 0, I get 1, so on and so forth. Then the last one is also very easy. We get 1, a, which is the base. So if I raise 2 to the power of 1, I get 2, right? If I raise 5 to the power of 1, I get 5. You raise something to the power of 1, you just get the number. So using this kind of function here, I would have -1, 1 over 2. I would have 0, 1, and I would have 1, 2. Now, these aren't enough points to get the full graph, but it's enough to kind of get things started. Now, before we get into some graphs, I want to talk about the restrictions involved with the base. And I want to tie this into the domain and the range and explain why there's an asymptote at the kind of x-axis. So you'll have a horizontal asymptote there. So let's start out by just listing this guy again. So we have f of x is equal to a, which is our base, raised to the power of x. And the restrictions are that a, the base, has to be greater than 0, and also a, the base, cannot be equal to the number 1. So first and foremost, we're given the fact that the domain is the set of real numbers. So from -infinity to +infinity, I can plug in whatever I want for x. There's no restriction. But that comes at a cost to us because we have to now restrict a because we're not restricting what gets plugged in for x. Let's say, for example, we allowed a, the base, to be something that was negative. So let's say we had -2, for example. Well, if I plugged in something like 1/2 or 1/4, you'd run into an issue in the real number system. -2 raised to the power of 1/2 is the square root of -2, which in the real number system, we don't have that, okay? Same thing goes if I raise it to the 1/4 power or the 1/8 power or something like that. So because we want the domain to be all real numbers, we've got to restrict the base. If we think about the number 0 itself and the number 1, then basically we restrict these because you wouldn't have an exponential function, okay? If you think about 1, let's say you had f of x is equal to 1 to the power of x. Well, no matter what you plug in for x there, if it's -0 or 1, you just get 1 here. So this is basically going to go down to y equals 1, which is just a horizontal line, right? That's not an exponential function. If you had something like, let's say, 0 to the power of x, well, this leads to all kinds of problems. First off, it's only defined where x is greater than 0, okay, because 0 to the power of 0 is undefined. And then if x was negative, let's say it was -1, well, 0 to the power of -1 is 1 over 0. That's undefined as well. And again, if you use negative exponents, that's going to keep happening. So it's only defined where x is greater than 0. And if you do plug something in that range, well, anything you plug in there, let's say you plug 1 or 2 or 1,000,000, you're just going to get 0, right? 0 to the power of 1,000,000 is just 0. So that's why that's restricted. Okay, so that takes care of this and this. So now let's think about the range. Why does it have to be greater than 0? Well, the reason is because if you think about this, and let's just write this as y equals a to the x for right now. And let me just use a practical example and just say 2 to the power of x. Okay, so let's say I was plugging different things in for x and getting a value for y. Let's say I started with a positive number like 2. 2 squared is 4. Okay, so that's positive. If I kept going, I would just get positive numbers if I'm plugging in positive numbers for this. Now, if I plugged in 0, I would get 1. What happens when I plug in negative numbers? Well, if I plug in something like, let's say, -2, okay, then over here, this is going to be what? It's 1 over 2 squared, which is 1/4. If I plugged in, let's say, -5, this is 1 over 2 to the 5th power, which is 1 over 32. So by increasing the negative here, so the way to think about this, because as you move to the left on the number line, the negatives are getting bigger and bigger, right? Bigger in terms of being more negative. That's what I'm saying. They're actually smaller because we're moving left on the number line. But as we get bigger and bigger negative numbers, this guy gets closer and closer to 0, but it will never actually get there, okay? So you can think about 2 to some incredibly large negative number. So 2 to the power of negative, let's say 100,000, for example, something like that. That would be really close to 0, and you can get as close as you want. You could do 2 to the power of negative 1 trillion if you wanted to, okay, and see what that is. It's going to be really, really close to 0, but you'll never actually touch it. So because of this fact, your y values in this function will approach 0, but they will never touch it, and so it forms a horizontal asymptote, okay, where y is 0, so at the x-axis. Now, if you have a problem where you have some shifting involved, this may change, okay? But generally speaking, if you get the f of x equals just some number raised to the power of x, you're going to have the horizontal asymptote that occurs at the x-axis. Now, let's actually look at the first example. I've already pre-drawn all of these because I'm a terrible drawer and these things are hard to draw. So I'm going to start with f of x is equal to 2 to the power of x. This is a typical example you'll see in your textbook. And the basic way to do this is just start out with kind of making a table of values, just like you've always done. So you know those 3 points already. You know that there's -1, comma, you're going to have 1 over the base. The base is 2, so 1/2. So that's a point. And we can go ahead and plot that. So -1 for the x and then 1/2 for the y. So that's there. And then you know you have 0 and then 1, right? If I raise 2 to the power of 0, I get 1. So the x value is 0 and the y value is 1, so that's right there. And then we know we have a value of 1 for x. That gives me a value of 2 for y, right? 2 to the first power gives me 2. So an x value of 1 and a y value of 2, so that's right there. And then I would just need to get some additional points going to make the graph clear. We know going to the left that it's going to approach the x-axis but never touch it. So I know if I chose some values, let's say I picked -2, for example, well, this is 1 over 2 squared, so that's 1/4. If I picked -4, this is 1 over 2 to the 4th power, so that's 1 over 16. Again, so on and so forth. So as this goes to the left, and I'm picking bigger and bigger negative values for x, the y values are getting closer and closer to 0, but they'll never touch it. You don't need this. You can get rid of this. You're just going to draw it to where it approaches 0 but doesn't touch it. And basically what I would do is get these points here. So just think about the integers that are left. If I go from 1 and go to 2, well, 2 squared is 4. And then I would go to 3. 2 to the 3rd power is 8. So that's enough for this guy. You can go to an x value of 2 and a y value of 4, and then an x value of 3 and a y value of 8. So that would give you enough points to sketch this graph. Again, it takes off very quickly. And with f of x equals 2 to the power of x, it's one that you can graph with your kind of graph paper. Let's look at one that takes off more quickly. So now we have f of x is equal to 3 to the power of x. And you'll notice that it takes off more quickly. Okay, so it's harder to get points here because typically you're going to work with a coordinate plane that the max y value might be 10 or 15 or something like that. If you think about 3 to the power of x, well, if I take 3 squared, that's 9, but 3 cubed is already 27. So that's way off the page, right? If you do 3 to the 4th power, it's 81. So that's just accelerating very, very quickly, right? So we know that, again, going to the left, it's the same phenomenon. It's going to approach a y value of 0 but never touch it. So we know how to draw that part. And then for the ordered pairs, again, I would just start with what we know. -1 and then 1 over the base, so 1/3. 0 and then 1, 1 and then 3. And then you could do 2 and 9, okay? But that's basically where you'd stop because, again, if you do an x value of 3, you're going to get a y value of 27. You could maybe do that on a graph paper if you started really, really low, okay, and you didn't really include this. Then maybe you can get to that, but that's still pretty hard to do. We have -1 for the x value and 1/3 for the y value. And we have 0, 1. So 0 for the x value, 1 for the y value. And then 1 for the x value, 3 for the y value. And then 2 for the x value and 9 for the y value. So that's enough points to get an idea of what this guy looks like and sketch your graph. All right, let's talk about some reflections now. So we understand what a reflection is. We get that if you have a graph that's f of x and then g of x is defined as the negative of f of x, this is a reflection across the x-axis. And then if g of x is equal to f of negative x, this is a reflection across the y-axis. So in this case, we have a reflection across the y-axis. We can see that. And so what's going to happen is I'm going to define f of x as 2 to the power of x. And then g of x is going to be f of negative x. So basically we could say g of x is equal to 2 to the power of, I'm just plugging in a negative x in the place of x. So this is going to be a negative x up here. Now, there's another way to look at this, and I'll talk about this. I'm going to graph this separately in a moment. But right now, let's just think about it as a reflection. So we already know these points because we already graphed this before. So you have this 3, 8. You have this 2, 4. You have this down here, which is 1, 2. And then over here, you have this point here, which is 0, 1. That's going to be on both of them. And then lastly, you have this one, which is going to be negative 1, 1/2. So to reflect this, I'm going to keep the y value the same. So over here, the y value is the same, but the x value will be its opposite. So you'd have negative 3, right? Just change 3 into negative 3, and then the y value is the same. Then this point over here. So the y value is the same, so it's 4. And then I'm going to change the x value into its opposite, so just negative 2. And then down here, so on and so forth, it would be negative 1, 2. And it's kind of hard to fit that in there, so let me just try. So negative 1, 2. And then if I go down here, this guy gets flipped over. So this would be positive 1 and then 1/2, okay? And then you have this point here that's on both. So you have that 0, 1 that would be on both. So if you wanted to graph this without reflecting it, it would be fine. You could do f of x is equal to 2 to the power of negative x. And realize that this guy could be graphed in its current state, or you could kind of manipulate this with exponents. And you could write this as 1 over 2 to the power of x. And 1 to the power of x would still be 1. So I could really say this is 1 to the power of x over 2 to the power of x. And I can now write this as 1 over 2, all raised to the power of x. Okay, so you can look at it this way or this way. Let me just kind of erase all this. This is just getting us there. Whichever way you find to be easier, I'm just going to work with it in this format. So kind of getting some ordered pairs going. I know my 3 points are going to be available to me. So my negative 1 and then 1 over the base. The base is 1/2, so 1 over 1/2 is 2. I know my 0, 1 is there, right? 0 for x, 1 for y. And I know my 1 and then the base is 1/2, so that's there. So those are my 3 points. Now, this guy is an example of where in nature we would say it's a decay graph. Okay, so it starts out high and goes low. The other ones are a growth graph, right? They start out low and they go high. So in this case, what I'd want to do, if I want to get some points up here, kind of going up, I need to go in the negative direction in terms of x. So I would go something like negative 2 and negative 3. And of course, we know that if we plug in a negative 2 there, 1/2 raised to the power of negative 2, through the rules of exponents, we know that would be 2 squared, right? That's all that is, which is 4. So this would be 4, and the same thing, 1/2 raised to the power of negative 3, through the rules of exponents, we know that would be 2 to the power of 3, or 8. So we saw this by reflecting it, but we see it by kind of plugging in the points here. It's the same thing. So if you want to kind of plot these, let's start with the 0 for x and 1 for y. And then we have that an x value of 1 would give me a y value of 1/2. And let's kind of go to the left now. So we would have an x value of negative 1, which would give us a y value of 2. And then an x value of negative 2 would give us a y value of 4. And an x value of negative 3 would give us a y value of 8. So again, that's another way you could sketch the graph of this guy. Once you have your points plotted, you could sketch this down like this. And of course, it's going to approach a y value of 0, but again, not touch it. So these are always going to approach the x-axis, but not touch them. In the case of a decay graph like this, it's going to approach it coming to the right. If you go back to your example with the growth graph, you see that it approaches it as you go to the left. So it starts out small if you're coming from the left and going to the right, and then it grows like this. So this is a growth graph. And again, because this one starts out high and comes down, this is a decay graph. All right, let's look at another reflection. So this guy is going to be reflected across the x-axis. So we know that, again, if we would define something like f of x to be equal to, in this case, it's going to be 3 to the power of x, well then my g of x here, if it's reflected across the x-axis, it's defined as the negative of f of x. So in this case, it would be the negative of this. So the negative of 3 to the power of x. So let me just erase this and put the negative of 3 to the power of x. And of course, now we're reflecting the points across the x-axis. So what happens is the x values stay the same, but the y values are now made into their opposites. So if I have this point here, which is 2, 9, and I reflect it across the x-axis, it becomes, again, 2, negative 9. So the x value now stays the same. The y value gets turned into its opposite. Similarly, this point right here, which is 1 comma 3 is going to become what? It's going to become 1, x value stays the same, and then negative 3. Then this point right here, which is 0 comma 1, so this is 0 comma 1, is going to get reflected across, and it's going to become 0 comma negative 1. And then this last point here, which would be negative 1, let me write this over here. So negative 1 comma 1/3 would be reflected across. So it's still an x value of negative 1, but now the y value is going to be negative 1/3. Okay, so on and so forth. So you can see that's a good way to kind of reflect it and sketch the graph. You could also graph this guy on its own. You don't need to reflect it. So let's say g of x, or you could say f of x, it doesn't matter. It's the negative of 3 to the power of x. Now you got to be careful here because basically you're taking, in terms of the y values that you're used to, and you got to make them negative. So those 3 points that you're kind of working with all the time, the negative 1 for x, and then the 1 over the base, well, now you got to make that negative. So instead of 1 over 3, it's got to be negative 1 over 3. Okay, so you got to keep that in mind if it's a reflection. And then if I had 0 comma 1, well, now it's 0 comma negative 1. If I had 1 comma 3, well, now it's 1 comma negative 3, so on and so forth. So I can do my 2 here, but now instead of getting 9, I get negative 9. Okay, so just keep in mind that you can work with the normal x values, but you've got to make the y values into their opposite. So again, just taking these 4 points, if I do negative 1 comma negative 1/3, that's there. 0 comma negative 1 is right there. 1 comma negative 3 is right there. And then 2 comma negative 9 is right there. So again, that's enough to sketch your graph. You know this guy going to the left is going to approach the x-axis but not touch it. And coming to the right, we're just going to go through those points. And again, you just draw a smooth curve, put an arrow at the end. All right, so I want to do one more of these. This is pretty typical in this section. We looked at some reflections, but you're also going to have horizontal and vertical shifts like we talked about earlier. So let's say f of x, which is my guy in yellow, is going to be 2 to the power of x. We already know that graph. We're comfortable with it. Now let's say we have g of x, and this is equal to 2 to the power of x plus 1, and then minus 1 over here. Okay, so we're going to have a horizontal shift 1 unit to the left. That's what that plus 1 is going to do right there. Let me highlight that. And you're going to have a vertical shift down by 1 unit. That's what that minus 1 is going to do. Remember how you think about this. We could say that g of x is equal to f of, in this case, it would be x plus 1 and then minus 1. Okay, so what's happening is this plus 1 here, again, you've got to think about the opposite of that if it's getting plugged in for x. So to undo that, this is the one that confuses everybody. So if it's associated with x, you undo it. So the plus 1, you got to go minus 1 to undo it. So it's a shift to the left. Let me just do this. Shift to the left by 1 unit. Okay. And then this one that's outside of the function, this minus 1, this just directly affects the y value. So we're just shifting down by 1 unit. So we'll say down by 1 unit. Okay. So if you've got a graph of f of x equals 2 to the x already drawn, and you just want to kind of shift this guy down by 1 unit and to the left by 1 unit, it's pretty easy to do. So just get your points going. So this point right here, which is 3 for the x value and 8 for the y value, gets shifted 1 unit to the left and 1 unit down. So now what is this going to be? Let me write this over here. Well, the x value is left by a unit, so it's 1 unit less, so it's 2. And the y value is 1 unit less, so it's 7. Then if I take this point right here, which is 2 comma 4, again, if I shift it, it goes 1 unit to the left and 1 unit down to get me right there. And so that is going to be 1 comma 3. Then if I take this point right here, which is 1 comma 2, again, if I shift this 1 unit to the left and 1 unit down, it ends up being what? 0 comma 1. Now that ends up intersecting with another point that's there, so that's a little bit confusing. But this point is already there on the original one, and that point of 0 comma 1 gets shifted down. So let me write this twice. So let me put 0 comma 1 over here. So this 0 comma 1 that's on the graph of f of x equals 2 to the power of x would get shifted 1 unit to the left and 1 unit down. So that's this guy right here, okay? That's crossing through the x-axis. And basically that's going to be what? It's going to be negative 1 comma 0. And then lastly, if you can see, I have this last point here, which is negative 1. And let me just draw an arrow for that one. So it's negative 1 comma 1/2. Well, that's going to go 1 unit to the left and 1 unit down. So that's going to be what? Negative 2 comma. And then if I took 1/2 and subtracted away 1, I'd be at negative 1/2. Okay, so I know this is messy, but again, if you're trying to show these kind of reflections or shifts or whatever it is, you just want to kind of mark things up and draw your other graph. It doesn't have to be perfect. You just want to show the teacher that you understand what's going on. In this lesson, we want to talk about solving exponential equations with like bases. So we just got done talking about exponential functions in general, and now the next topic is to discuss how we can solve exponential equations when you have like bases. So we're not going to involve kind of logarithms yet. We'll see that in a few lessons. So for now, we just want to use this rule to solve some problems. So if a to the power of x equals a to the power of y, then we can say x equals y. So what does this mean? Well, as long as a, this base here, is greater than 0 and it's not equal to 1, then basically if these bases are the same, meaning I have the same number here as I have here, well then I can just set x equal to y and I can solve. So if you have the same base, then you're just going to set the exponents equal to each other and solve the resulting equation. So it's easy enough. Let's just kind of jump right in and look at an example. So we have 2 to the power of 5x minus 7 is equal to 64. So when you see problems like this, again, a lot of it is just making you kind of think through your properties of exponents. You should know at this point that 64 is 2 to the 6th power. If you didn't, always look at this number over here, the one that's kind of simpler. If you have something that's a prime number like 2 or 5 or 7, check to see if the number on the other side is divisible by that. So I know 64 is divisible by 2. If I set up a little factor tree, then I'm going to go through and find out that it's 2 to the 6th power. So what happens is I can now rewrite my problem and say this is 2 to the power of 5x minus 7. And this equals, instead of 64, I'm just going to write 2 to the 6th power. So now, through a little bit of manipulation, I have like bases. So I have 2 and I have a 2. So what I want to do now is just set these exponents equal to each other and solve. Very simple process. So 5x minus 7 is equal to 6. We're just going to add 7 to both sides of the equation. And of course, this is going to cancel, and I'll have 5x is equal to 13. Divide both sides by 5, and you get x is equal to 13/5. All right, so let's go ahead and look at another one. So we have 1/7 raised to the power of 6x equals 343. Again, if you're in this section, the idea here is that you're going to be able to rewrite things in such a way that you're going to have like bases. So 7's a prime number, so that should be a little hint for you that, hey, is 343 divisible by 7? You check that on a calculator, it is. 343 divided by 7 is 49. Divided by 7 again, you get 7. So that tells me 343 is 7 cubed. So I know that on the right side, I could just say this is 7 cubed. Now on the left side, I don't have 7. I have 1 over 7. But again, here's where you got to use your rules of exponents. I know that 1 over 7 is equal to what? It's 7 to the power of negative 1. Remember that little rule. So the first thing I'm going to have to do, this is going to be 2 steps. I'm going to say that 1 over 7 is 7 to the power of negative 1, but then it's raised to the power of 6x. Now, what I want to do is I want to use my power to power rule, and I want to say, okay, if 7 is raised to the power of negative 1, and then it's raised to the power of 6x, the base here stays the same. I multiply exponents. So all this is going to be is negative 1 times 6x is my exponent, and that'll just be negative 6x. So most of the problem here is just setting things up, okay? After you've got that done, a lot of these are really, really simple equations to go through. So I'm going to set this equal to this and just solve it. You can almost do that mentally. So negative 6x equals 3. Divide both sides by negative 6, and we're going to get that x is equal to what? This cancels, and 3 over negative 6 is a half, and you've got that negative there, so it's negative 1/2 as your answer. All right, let's look at one that involves a little bit more work. So we have 216 raised to the power of negative 4x plus 7 equals 36 raised to the power of 2x plus 1. So if I look at this now, neither of the bases are a prime number, so I've got to start to think in my head how I can relate these two. What would the like base be? Okay, so 36 I know off the top of my head is 6 times 6, right? So once I figure that out, then I can look at 216 and say, okay, is that divisible by 6? Yeah, 216 divided by 6 is 36. Well then, okay, 216 is 6 cubed. So you're going to have 6 cubed, and then this is raised to the power of negative 4x plus 7. And this equals, you're going to have 6 squared, and this is raised to the power of 2x plus 1. So here's where people start to make mistakes. Make sure that this 3, when you do your power to power rule, gets multiplied by the whole thing. Make sure that 2 over here gets multiplied by the whole thing. So let me kind of break this down so you don't get lost. So power to power rule tells me that I'm going to multiply these two exponents. So 3 gets multiplied by this quantity. So 3 times the quantity, negative 4x plus 7. Make sure you use parentheses, because if you don't, you're going to make a silly mistake. This equals 6 to the power of what? Use parentheses. 2 times the quantity, 2x plus 1. Okay, so once we've done this, now we're just going to simplify. I've got 6 to the power of 3 times negative 4x, which is negative 12x. And then plus 3 times 7 is 21. This is equal to 6 to the power of what? 2 times 2x is 4x. And then plus, you've got 2 times 1, which is 2. Okay, so we've done all that work to get it in the format where we can use our little rule. We've got 6 and we've got 6. So we've got like bases. So now what I want to do is just set my exponents equal to each other. So I'm going to take this one, set it equal to this one. Very simple. So negative 12x plus 21 equals 4x plus 2. I'm going to go ahead and subtract 4x away from both sides of the equation. And this is going to cancel. I'm going to subtract 21 away from both sides of the equation. And this is going to cancel. Let me get more room. So now what I'm going to have is negative 12x minus 4x, which is negative 16x. And this equals 2 minus 21, which is negative 19. To finish this up, let's divide both sides by negative 16. And let's just go ahead and cancel this out. And we'll say, I'll just write this up here, that x is equal to negative 19 over negative 16. That's just going to be 19 over 16, right? 19 is a prime number, so nothing you can really do to simplify there, unless you want to write it as a decimal. Okay, let's look at the next one. All right, now we have one that is a little bit more complicated. So each of these is kind of grown in complexity. So we have 32 raised to the power of 5 minus 3x times 64 raised to the power of negative 2x minus 1, and this equals 1 over 8. So if you look at 32, you look at 64, and you look at 8, you should be thinking immediately about a base of 2, right? Because 2 cubed is 8, 2 to the 6th power is 64, and 2 to the 5th power is 32. So if I just start with this 32 and say this is 2 to the 5th power, then raised to this 5 minus 3x. Let's just go ahead and crank this out real quick. Again, power to power rule, this is going to get multiplied by each one of these. So remember, to do this, you would multiply with this guy in parentheses. So 5 times 5 is 25, and then 5 times negative 3x is minus 15x. So I'm just going to erase all of this and use this as my exponent. So 25 minus 15x. Okay, so this one, 64, is 2 to the 6th power. So 2 to the 6th power, again, this is raised to this guy, negative 2x minus 1. Power to power rule. 6 is going to get multiplied by each of these. So what I'm going to do, I'll just do this down here. You wrap this in parentheses. So 6 times the quantity negative 2x minus 1. This equals what? This is going to be 6 times negative 2x. That's negative 12x. And then 6 times negative 1 is minus 6. So let's go ahead and erase all of this. And I'll say this is to the power of negative 12x and then minus 6. Okay, so let's just stop for a minute. We'll figure out the right side in a moment. Remember our rule for kind of multiplying when exponents are involved. If I have a to the power of m times a to the power of n, this is a to the power of m plus n. Well, it's the same thing here. I have like bases. I have a 2 and I have a 2. I'm multiplying. So all I'm going to do is I'm going to say that this is 2. Okay, this is 2 raised to the power of, I'm going to add these exponents together. So let me write this as plus negative 15x, and I'll say negative 15x minus 12x is negative 27x, and then I'm going to do 25 minus 6, which is 19, okay? So that takes care of that, and you can even erase this at this point. So this is the left side, as simple as we can make it. Now for the right side, I have 1 over 8, and remember, I can say this is 1 over 2 cubed, but we know that this is not 2. This is 1 over 2 cubed. Now, I want you to think about the fact that you could write 1 over 2 cubed using a negative exponent by saying this is 2 to the power of negative 3. Again, if you drag this into the denominator, everything stays the same. You just change the sign of the exponent, okay? So that's our rule from earlier in the course. So I'm going to write this as 2 to the power of negative 3. And again, the main part here is just getting things set up. So now this is going to be equal to this because I do have like bases. So I would say negative 27x plus 19 equals negative 3. And then from here, let me scroll down and get a little room going. I would just subtract 19 away from each side of the equation, cancel this, and say negative 27x is equal to negative 22. Divide both sides by negative 27. And what's going to happen is this cancels with this, and I'll have x is equal to, I'll have 22 over 27. Because again, negative over negative is positive. If you think about 22, it's 11 times 2, and 27 is 3 cubed, so no way to really make that any simpler. All right, let's wrap up the lesson with one that seems kind of easy, but does trip up a lot of students. So we have 4 is equal to x to the power of 2/3. So you might also see this in this section. What in the world do you do to solve this? There's no way to really get like bases, right? Because this is 4 and this is x. So what you want to do here is think about this using kind of a radical notation that we learned earlier. So I'm just going to go ahead and say this is x, and I want the cube root of that. And then this whole thing is going to be squared, and I'm going to set this equal to 4. Okay, so this is just another way to write the x to the power of 2/3. This is going to be what it's raised to, and this is going to be your index on your radical. Okay, so what could I do to clear this 2 up here? Well, I could take the square root of both sides. So I could take the square root of this side, and then over here, let me kind of slide this down. Remember, if you're taking the square root over here you've got to go plus or minus the square root. So now I know this would cancel with this, and I'm just left with that. And so what I would have is just the cube root of x is equal to plus or minus 2. So let's erase this. Let's think about what this means. We have the cube root of x is equal to 2, or we have the cube root of x is equal to negative 2. So there's 2 scenarios. Now, what I can do from here is just cube both sides in each case to get rid of this kind of radical. So I'm going to do that over here as well. And what I'm going to find is that what? Well, here I just have x is equal to 8. And then over here, I would have x is equal to negative 8. So I can simplify that and just say x is equal to plus or minus 8. And this is a good one to check because it's kind of one that you have to think about for a while. So if you plug in an 8 here, and I say, what is 8 to the power of 2/3? Well, let's think about that. What is the cube root? Let me make that better. What is the cube root of 8? Well, that's 2, right? And then if I square that, I'm going to get 4. So this becomes 2, and then if I square it, I get 4. So that one checks out. What if this was negative 8? Okay, what if it was negative 8? Well, what I would have is the cube root of negative 8, which is negative 2, and we would put parentheses here because this amount, this quantity of negative 2 would be squared, okay? And so we'd have negative 2 squared, and that would also give me 4. Okay, so keep in mind you have 2 solutions here. It would be x equals positive 8 and also x equals negative 8. And I'll just write that one more time. So x equals plus or minus 8. In this lesson, we want to talk about the compound interest formulas. So when you talk about kind of exponential functions, somewhere in this section, you're going to run into this topic of compound interest. Now, we talked about the simple interest formula earlier in the course. Now we're going to be able to talk about compound interest, which is where you earn interest on interest. So the formula goes like this. We have A is equal to P times the quantity 1 plus R over N, and this guy is raised to the power of T times N. So this process here is very, very straightforward. Okay, you just need to understand what each letter in this formula represents. So A is the future value. So what we're saying here is this is the account balance in the future. If I have an investment for 5 years, at the end of the 5-year period, A, this here, would be my future value or the account balance at that time. P is the principal, or you could say the present value. It's how much the kind of investment is worth right now today. How much am I putting into the bank or the CD or whatever it is. And then R is the rate as a decimal. So if you have 10%, it's 0.1, 5% is 0.05, so on and so forth. T is the time in years. That's really straightforward. And then N is the number of compounding periods per year. So this is one that you do have to kind of know off the top of your head. So if they say something like it's compounding monthly, well, we know that in a year there's 12 months, so that number is going to be 12. If it was semi-annually, well, that means twice in a year, so we would put that number as 2. So on and so forth. Something like quarterly would be 4, right? 4 times per year. So let's use this formula to kind of calculate this example. So we have Jamie invests $3,155 in a CD, which is a certificate of deposit, with an annual interest rate of 4% compounded quarterly. Let me go ahead and highlight that. It's quarterly, so 4 times a year. What is the account balance after 5 years? So basically with this, you're just plugging some stuff in, and then you're going to use your calculator to get an answer. You just have to make sure to follow the order of operations. As long as you understand what you need to plug in, this is super simple. So again, our formula is that A is equal to P times the quantity. We have 1 plus, you have R over, and then we're going to have N, and then this guy right here is raised to the power of N times T. So Jamie invests this amount right here, this $3,155. That's the current value or the present value of the investment, or you could say the principal. So that's your P. So I'm just going to, instead of erasing it, let me just kind of draw an arrow and say this is going to be 3,155. And then when we go over here to R, that's the rate as a decimal. So my rate is right here. It's this 4%. As a decimal, let me kind of draw an arrow. This is going to be 0.04. And then we say it's compounded quarterly. Again, think about a quarter as being what? It's a fourth of a dollar. Okay, so if you had 4 quarters, you'd make $1. Well, it's the same thing. You have 4 quarters in a year. Okay, so when we say the N is the number of compounding periods, here that's going to be 4. And I'm just going to plug that in here as well. And then T is the number of years. That's here, right? It's 5 years. So really, once you understand what each letter is for, you just write your formula out and you plug in, and then you just do the calculation. It's really, really simple. So let's come down here. And we'll say A is equal to, now I'm just going to plug in. So I'm going to say 3,155 times the quantity. I'm going to have 1 plus, I'm going to have 0.04 divided by 4. And this is raised to the power of 4 times 5. We'll go ahead and just write that as 20 for now. And then let's come down here and see if we can simplify this a bit. You could plug this into your calculator right now, but I'm going to tell you, if you don't know the order of operations, you need to really revisit that topic, okay? Because if you just plug it straight into the calculator, a lot of times you're not going to get the right answer, okay? So let's just go ahead and simplify this as much as we can. So I'm going to say A is equal to 3,155 times, what is 0.04 divided by 4? That's 0.01. So this would be 1 plus 0.01, and I'll just go ahead and say that's 1.01. So this is 1.01, and this is raised to the power of 20. Okay, so now it's very straightforward. All I have is multiplication, and I have an exponent operation. Again, we know our PEMDAS, or our order of operations. We raise to the power first, and we take that result and multiply it here. But if you punch this into your calculator at this point, it's not going to make an error. It knows that if you do 3,155 times this raised to this, it'll do the exponent first, and then it'll multiply. So let's go ahead and crank that out and see what we get. So on my calculator, I get 3,849, and then I get 0.69956. Now with these problems, you're usually going to round to kind of the hundredths place. So what I want to do is think about this number here. It's a 9. So I know I'm going to round up. So I'm just going to make this a 70. So I'm going to just say that this is going to be $3,849.70. Okay. And yeah, that's an approximate amount, but in real life, this is what they would do. You don't get an amount past this when you work with real money, right? You would just stop at 70 cents. And so we're just going to copy this, and I'll just paste this in here. We could just say the account balance is, and we'll say $3,849.70. And you can even put after 5 years. And keep in mind, we did round this, but on this type of problem, you're expected to round. So this is definitely the correct answer. All right, let's take a look at another one, and we can blow through this one now. So Robin invests $12,000 in a bond fund with an annual interest rate of 6% compounded quarterly. What is the account balance after 11 quarters? Well, again, I want the formula A is equal to P times the quantity 1 plus R over N raised to the power of T times N. Again, what is all this stuff? A is the kind of future value of the investment. So after the time period, in this case, it's going to be 11 quarters. So we don't know that. That's what we're trying to solve for. P is the principal or amount invested. In this case, Robin invests $12,000. So $12,000, okay, times this quantity here. We have 1 plus R, which is the rate, okay? So that's 6%. It's put in as a decimal, so 0.06, or you can put 0.06 if you want. And then this is over the number of compounding periods, again, in a year. It tells us that it's compounded quarterly. So this is going to be, again, 4. Now, here's where it gets a little tricky. You have this t times n. T is the time period in years. We're told this guy in quarters, okay? So let's get to that in a second. We know n is already 4. So if I have 11 quarters, how many years is that? Well, the quick way to relate this in your mind is to think about, okay, if I had 11 quarters in money, how much would that be in dollars? It'd be $2.75, right? You could do that pretty quickly because you know 12 quarters is $3. But if you didn't do that, the official way is to set up a little unit fraction and say, okay, well, I know that 1 year is equal to 4 quarters. And so I could say 1 year over, let me just erase this, 4 quarters has a value of 1, right? Because these two things are equal, I can write the same non-zero quantity over itself. Okay, it's going to give me 1. So I can then multiply this by 11 quarters. And what's going to happen is these units that I don't want are going to cancel. So I would have 11 divided by 4, which would give me 2.75. So if I come back up here, I can just say this is 4 times 2.75. And if you do that on a calculator, you're going to get 11. Okay, so let's bust this out real quick. Just pull out your calculator. Again, to not make a mistake, I always recommend to simplify what's inside the parentheses first. Because if you punch this in on your calculator and you're not paying attention, you're going to get the wrong answer. So 0.06 divided by 4 is 0.015. So let's erase this and just temporarily put 0.015. And of course, if I add 1 plus 0.015, it's just 1.015. So from this point, you could just raise this to the 11th power in your calculator and multiply that result by 12,000. You're going to get 14,135. Again, you get a long decimal, so 38725. But we're going to go ahead and round this. Again, I'm just going to round it to the nearest hundredths. So I'm going to think about this guy, okay? And so since this guy is a 7, I'm going to round this to a 39 there, okay? So I'm just going to erase all this, and I'm going to erase this, and I'm going to make this into a 9. And I'll put my $sign out in front. And again, you can make a nice little sentence and just say that the account balance is, and I'll just drag this up here, $14,135.39 after, you could say 11 quarters or 2.75 years. All right, so another type of problem you're going to see in this section involves finding the present value. We have that Ned's savings account has a current balance of $6,000. If Ned opened the account 5 years ago and received an annual interest rate of 1.8% compounded monthly, what was the opening balance of the account? So this is very, very simple. You use the same formula. Again, A equals, you've got P times the quantity 1 plus R over N raised to the power of T times N. Okay, so let's think about this for a second. We don't have P anymore. That's what we want to solve for. We want to solve for that. Now, at this point, you could divide both sides by what's multiplying P, but I would just hold off on that for 1 second, and I would just plug some stuff in. So this is not all going to fit on the screen, so I'm just going to go back and forth. So the future value here, or the account balance in the future, or when the investment is done, is $6,000. That's given to me right there. So let's scroll down for a minute, and I'm just going to write $6,000, or 6,000. And this will be equal to, again, we don't know what P is. That's what we need to solve for. So then times, we have 1 plus, what's the interest rate? Let's go up. So we have 1.8% and it's compounded monthly. My R is going to be 1.8% as a decimal, which is, you can put 0.018. And then when we say compounded monthly, this N here is going to be 12, right? Because there's 12 months in a year. So let's put a 12 there. And then this guy's going to be raised to the power of T times N. We know N is 12 already. What's T? Let's go back up, and it says 5 years ago. So he had this guy for 5 years. So let's go back down and put a 5 here, and now we're basically ready to go. So all we're going to do is kind of simplify this inside. So if I divide 0.018 by 12, I'm going to get 0.0015. So I'm going to get 0.0015. If I add that to 1, I'm just going to put a 1 out in front. So that's pretty simple. So I know 12 times 5 is 60, so let's take care of that. And now, all I need to do, let me kind of scroll down and get a little room going. I'm going to divide both sides by this amount. So I'm going to divide this side by 1.0015 raised to the power of 60. And let me just kind of slide this down and slide this down so I have enough room. And then I'm going to divide this side by that as well. So 1.0015 raised to the power of 60. We know that the same non-zero number divided by itself is going to cancel to become 1. So P will be by itself now, okay? And it's equal to this, 6,000 divided by this number here, 1.0015 raised to the power of 60. So if you punch that up on a calculator, you're going to get that P is equal to 5,483. You get 0.956896. So we're going to round this. Again, if I look at this digit here, it's a 6. So I'm going to cut this off and just put this as a 6 here. And you can put an approximate symbol here if you want, because it's not exactly equal when you round. But we just want to answer the question with this number here. So let me copy this, and I'm just going to erase all this. And again, you can make a little sentence if you want to. You can say the opening balance, let me drag this out, the opening balance, and we'll just say was, and we have this $5,483.96, and you can just put a period after it. That's good enough. The opening balance was $5,483.96. And if you wanted to check this, you could pause the video and take this number, run it back through, okay, the formula we've been using for the other two examples, and you'll see you get pretty much this amount. In this lesson, we want to talk about the continuous compound interest formula, the A equals P times our special number E raised to the power of R times T. So we've already worked with the compound interest formula, and we've already used it to solve some simple word problems. Let's just look at this real quick. We have A, the future value, is equal to P, the principal or present value of your investment, times the quantity 1 plus R, which is the rate as a decimal, divided by N, the number of compounding periods per year. And this guy inside the parentheses is raised to the power of T, which is the time in years, times N, again, the number of compounding periods per year. So if we want to kind of build up to this idea of continuously compounding interest, let's start out with what we know. So I have a basic example here so we can compare them. We have $1,000 is invested at an annual interest rate of 10%. Give the account balance after 1 year for the different compounding periods. So we've got quarterly, monthly, daily, and continuously. And we can just blow through this real quick. We know the formula. Let me just write it again. It's A equals, you've got P times the quantity 1 plus R over N raised to the power of T times N. Okay, so what you want to do is just plug in and use your calculator. It's really simple. So for quarterly, this is going to be compounded 4 times per year. So 4 times per year, they're going to give you your interest, deposit it in there, and then you're going to earn interest on that interest. Okay, so for the P, the principal, it's $1,000. It's the amount invested. And then this is times 1 plus, if you have R, that's the rate as a decimal, so that's 0.1. Then over N, which in this case is going to be 4, right? The number of compounding periods. It's raised to the power of T times N. Now in this case, our T, our number of years is 1. So you can just forget about that because multiplying by 1 is going to leave something unchanged. So we just put N there, which is 4. So if you punch this up on a calculator, you're going to get approximately, and I'm just rounding this number, $1,103.81. Again, I rounded this. So let's just put this, I'm just going to kind of slide this down. Let's put this over here. We'll say this is $1,103.81. Now, for a given interest rate and a given time period, if I increase the number of compounding periods or how often I give you your interest so that interest is earning interest, I should have more money, right, at the end of that kind of time period. So let's see this. So for monthly, all I want to do is put a 12 here and a 12 here. Everything else is the same. If you punch this up on a calculator, you're going to get about $1,104.71. Again, it's an estimate. We're just rounding. So let's go ahead and put this as $1,104.71. Again, we increased the number of compounding periods from 4 to 12, and we saw that we ended up with more money at the end of the year. Now, if we go with daily, that would be 365 days for a normal year. If it was a leap year, it would be 366. So in this case, if you punch that up on a calculator, you're going to get, again, if you round, about $1,105.16. So let's erase this formula. We don't need it anymore. So we have this, $1,105.16. Now, there is a theoretical maximum number of compounding periods that you can kind of get to. In other words, if we took this n here and we kept increasing it, right? Instead of 365, we went to 1,000, then to 1,000,000, then to 1,000,000,000,000. We just went towards infinity. What happens is as we're continuously getting interest deposited into our account, our money is continuously compounding, then the formula changes a bit, okay? And it involves our special number e. So we say A is equal to P times the special number e. Remember, that's about 2.718. Raised to the power of r times t. So the r, again, is the rate as a decimal. The t is the time in years. So this is a really simple formula to use. In this case, p, again, is the principal. So it's 1,000 times e. Okay, and that's going to be on your calculator. Raised to the power of r, which is 0.1, and then times t, which is 1. So really, you can just get rid of this part and say we have 1,000 times e raised to the power of 0.1. And if you punch that up on a calculator, you get about $1,105.17. So you can see it's very close to what we got with daily. And if you continued out, if you went with 1,000 and then 2,000 and 3,000, as you keep increasing the number of compounding periods, you get closer and closer to this kind of number that you get from this formula here. All right, let's look at another example. This is a very easy concept. Just memorize the formula and plug into it. That's all you have to do. So we have that James invests $2,000 in a savings account paying 3% annual interest compounded continuously for 7 years. What is the account balance at the end of the term? Very easy. Again, A equals P times E raised to the power of R times T. Most of this is just memorizing the formula. Hopefully your teacher lets you write it down on a piece of scratch paper. But basically, you're just going to plug in. So for P, I have 2,000. Then times E raised to the power of R times T. In this case, the rate is 3%. So as a decimal, it's 0.03. And then the time in years is 7. So it's times 7. So basically, 0.03 times 7, just think about 3 times 7, that's 21. You'd have 2 decimal places there, so it would be 0.21. And if you punch that up on a calculator, you're going to get approximately $2,467.36. So if you wanted to make a nice little sentence, you can. Let me just erase this real quick. We'll use that number. So we'll just say that James has, and I'll just kind of drag this up here. So $2,467.36 at the end of the term. All right, let's take a look at one more problem. Again, this is super simple. So Susan wants an investment with an annual interest rate of 6%, which is compounded continuously. A zero coupon bond can be redeemed in 5 years for $10,000. How much should Susan pay for this bond? So first and foremost, let me explain this zero coupon bond. In case you've never taken a finance course before, basically these trade at a discount. So they don't pay any interest. You're not getting any payments while you own the bond. You basically just get a discount to the kind of price that you're going to get at the end. So it would be like if you loaned me $50 and at the end of, let's say, 2 years, I gave you back $100. But during that 2-year period, you didn't see any money. So that's what this is like. So we know that, let me kind of write the formula down. Again, it's A is equal to P times E raised to the RT. We know that she wants to earn an interest rate of 6%. So I can go ahead and erase this and put 0.06. And we also know that this investment is for 5 years, so times 5. If you want to go ahead and do that, it would be 0.3 or 0.30 if you wanted to write that. So you can just put 0.3 here. E, we don't need to really worry about that. That's built into our calculator. But the P, the principal, is what? Well, that's what we want to solve for because we want to know how much should Susan pay for this bond. How much should Susan pay for the bond? We don't know. But we have the amount she's going to get at the end, right? At the end of this, in the 5 years, she's going to get $10,000. So I'm just going to erase this and put my 10,000 here. Put my comma in. And basically, I just want to solve for P. So I want to divide both sides by e raised to the power of 0.3, and I'll have my answer. So let me just kind of erase it from over here. And you can punch that up on a calculator. And what you're going to get, let me just kind of erase this, and I'll just do this over here. It's going to be approximately $7,408.18. So that's how much she should pay for the bond. Again, she wants a 6% annual interest rate where it's being compounded continuously, and it's a zero coupon bond. So she pays this amount, and 5 years later, she gets this amount. So let's go ahead and write that down as our answer and just say that Susan should pay, and I'm going to put this $7,408.18 just for the bond. In this lesson, we want to talk about logarithmic functions. So something like f of x equals a to the power of x is our exponential function, where again, a, your base has to be greater than 0 and also not equal to 1. We already talked about why those restrictions are important. But basically, from the lesson on graphing an exponential function, you saw that it would pass the horizontal line test, and therefore it's a one-to-one function, and every one-to-one function has an inverse. So basically, we would start by saying that f of x is y, and it would be equal to a to the power of x. Now, if you want to find the inverse, you swap x and y. So I would now say that I have x is equal to a to the power of y. And then from here, you would solve it for y and say you have f inverse of x. But there's a problem here. We don't really have a way to solve for an exponent until you introduce something known as a logarithm, okay? So a logarithm is an exponent. That's something you need to remember if you've never worked with logarithms before. So what I can do is I can write this in a different format in such a way that it allows me to solve for this exponent y. Okay, so I'm going to put y out in front. So y will be equal to, and then I'm going to have my logarithm here. So I'm going to have log with a base of a, and it's the same base for my exponential expression there. So the base is a, and then of, you're going to have this answer over here. So that's going to be x, okay? So basically the way this works, this is your base, and it came from this base here, okay? Then this guy right here, your exponent, is what you're solving for. So it's going to be out in front. So y equals this guy right here. Again, when you say it equals something, it means it's the same as. So y is the same as this log base a of x. That's why we're saying that a logarithm is just a fancy way to write an exponent. Then lastly, this x right here, when you work with it in a logarithm, you call it the argument. But really, to try to make this simpler, I'm just going to say it's the answer. Okay, so the answer, so a and s. So this is your answer from this original problem. So if you write that down, it's easy to kind of go back and forth between the forms. And if you get confused, write out this generically, and then you can kind of practice going back and forth. That way, when you get to the problems that don't involve kind of the same letters, you can go back and forth between your exponential form and your logarithmic form. Now, there's one thing that I want to note here. Okay, I want to just erase this real quick. If we look at this in kind of exponential form, this x equals a to the power of y, you'll notice that you need another restriction. So these restrictions are going to hold. So you're going to have that a is greater than 0. You're going to have that a is not allowed to be equal to 1. But also you're going to see that x needs to be greater than 0 as well. So this is another restriction you have to have when you're working with logarithms. And the reason for this is simple. If you take some number a, and again, we're working with something greater than 0 not equal to 1, and you raise it to some number y, and y can be any real number. It can be from negative infinity to positive infinity, so negative, 0, positive, whatever you want. Well, what happens is the result of this can never be 0, and it can never be negative. And it just has to do with the rules of exponents. If I have, let's say, 2 as an example as a, and let's say y is some negative number, let's say it's negative 2. We've talked about this previously. This is 1 over 2 squared, which is 1/4. So if you increase the negative, okay, meaning I go to the left on the number line, or I make it a bigger negative, this guy right here, this result just gets closer and closer to 0, but it's never going to actually touch it. Okay, so that's why we have this restriction here that x is greater than 0. So if you ever see a problem with the argument here as 0 or something that's negative, then you know they're trying to throw you a trap question. Okay, so that's not going to have an answer. All right, so let's look at this one more time. So we have our log form, y equals log base a of x, and our exponent form, x equals a to the power of y. Again, this is your base, this is your base. Okay, easy to remember. This is your exponent. Over here, it's solved for the exponent. That's how I keep track of it. I know that it's solved for the exponent in logarithmic form. And then this right here, again, your argument, you could really say it's the answer. So a to the power of y will give me an answer of x. A to the power of y will give me an answer of x. All right, so let's jump in now and look at some basic examples of kind of going back and forth between the exponential form and the logarithmic form. So I already have this laid out for us. The log base a of x equals y, just as a reminder. Again, this is a to the power of y is equal to x. So a to the power of y is equal to x. Okay, so here we have log base 2 of 4 equals question mark. So how do we figure this out? Well, we can convert it into exponential form, again, using the same process. So 2 to this question mark here, 2 to something is equal to, again, this guy right here, so 4. So we don't need to do anything fancy here. We know that 2 squared is 4. Okay, that's pretty obvious. So the question mark here would just be 2. Okay, so 2 squared equals 4. And we can write this in logarithmic form by just saying log base 2 of 4 is equal to 2. Again, it's solved for the exponent. See how this exponent here matches what it's solved for there. All right, let's look at one more. And for this one, I'm going to first put it into exponential form and then put it into logarithmic form. So 3 to the power of negative 2 we know is what? So 3 to the power of negative 2 is 1 over 3 squared, which is 1/9. Okay, so if I have 3 to the power of negative 2 equals 1/9, how can I put this in logarithmic form? Again, this is the base. Okay, this is the base. So you would have log base 3 of, what's my answer? It's this one, right? It's 1/9. So that comes in here. That's going to be the argument of the logarithm. So 1/9. And this equals what? It equals this guy. Remember, it's solved for the exponent. So the exponent is negative 2, so that goes on one side by itself. So log base 3 of 1/9 equals negative 2. 3 to the power of negative 2 equals 1/9. Again, different ways to kind of write the same thing. All right, let's wrap things up by looking at some very simple equations. As we move throughout this chapter, we'll see much more complicated examples, but we need to talk about the properties of logarithms first before we can get into that. So suppose we have log base a of x equals k, and then we transform this into what? A to the power of k is going to be equal to x. A to the power of k is equal to x. So we're going to use this in order to solve some of these problems. And we start with log base 3 of 81 equals x. So we're just going to put this in exponential form. So again, the base is 3. The exponent is x. So 3 to the power of x equals, the answer is 81. Okay. Now, some of you are saying, hey, you need logarithms to solve that. But remember, you don't. Because 81 can be written with a base of 3. I can say that 81 is 3 to the 4th power. And earlier in the course, we talked about the fact that if you had the same base, okay, if you had the same base, so 3 and 3, then the exponents, you would set those equal to each other and solve. In this case, you would just get x is equal to 4, okay? And you can prove to yourself that that's true. If I had log base 3 of 81 is equal to 4, well, yeah, 3 to the 4th power equals 81. 3 to the 4th power equals 81. What about log base 4 of x equals 7/2? Well, again, let's set this up in exponential form. So you've got your base 4. Raised to this power, again, it's solved for this, so raised to the power of 7/2, and this equals x, right? It equals this guy right here. Now, we don't need to do anything fancy here. We just need to figure out what is 4 to the power of 7/2. And remember, this guy right here can be written as what? 4 to the power of 7/2 is really 4 to the 1/2 power raised to the 7th power, okay? And 4 to the 1/2 power is the square root of 4, which is 2. So this is 2 to the 7th power, which is 128. So again, I could write this as log base 4 of 128, and this equals 7/2, because 4 to the 7/2 power gives me 128. All right, let's look at another one. So we have log base x of 1/8 equals 3. Again, we'd have x, which is the base, to the 3rd power equals 1/8. Okay, so for this one, I do need to do a bit of work. I need to take the cube root of each side. So I'll take the cube root of this side and the cube root of this side. And so this whole thing is going to cancel with this kind of exponent of 3. And I'm just left with x, and that'll be equal to what? The cube root of 1/8 is 1/2, because the cube root of 1 is 1, and the cube root of 8 is 2. So it's 1/2. So we can erase this, and we can basically say x equals 1/2, because log base 1/2 of 1/8 is equal to 3. Right? If I took 1/2 and I raised it to the 3rd power, I would get 1/8, right? 1 cubed is 1, and 2 cubed is 8. All right, let's take a look at a common trap question. So we have log base x of -5 equals 10. So whenever you see a negative or a 0 as your argument, you need to stop immediately, okay? This is a very common trap question. There will not be a solution here. Remember, your base for this guy is going to be restricted. It's got to be greater than 0, and it can't be equal to 1. Okay, so given those restrictions, if I set this up as x to the power of 10 is equal to -5, there's no such x, right? There's no solution here. That's not possible. Not possible. If I plug in something that's positive there, and again, not equal to 1, well, I'm always going to get a result that's positive, so there's no solution here. All right, so now let's kind of look at two harder examples, or you could really just say more tedious examples. They're not necessarily harder. So we have the negative of log base 5 of 7 minus 6x, and then outside of the parentheses, we have -2, and this is equal to -1. So if you get a problem like this, the first thing you want to do is write it in a familiar form. So we know that we can solve something like log base a of, let's say, x is equal to just something like b. Okay, we know that a to the power of b is equal to x, and we can solve stuff given that we only have one unknown, right? So for this one, I'm just going to put it into that format. So I want to take this part right here and set it equal to some number over here. So how can I do that? Well, what I want to do is I want to add 2 to both sides of the equation, and this will cancel. And that'll leave me with this negative here. I'm just going to write that as -1 times log base 5 of, you got this 7 minus 6x. And this will be equal to -1 plus 2 is +1. Okay, from here it's pretty simple because we just have the -1 that we got to get rid of because it's multiplying this guy over here. So I can either divide both sides by -1 or multiply both sides by -1. It doesn't really matter. If I multiply the left side by -1, then I would just clear that. It would just become 1. So I would have log base 5 of 7 minus 6x. And then over here, if I multiply this side by -1, and let me just kind of do this. So let me do this over here, and I'll put a times there. So these two would cancel and just give me 1. And over here, 1 times -1 is -1. Okay, so from this point on, it's pretty simple. Okay, once you kind of figure out how to get it in this format, then basically just do what we've been doing. 5 to the power of -1 is equal to this guy right here. Okay, so you'd have -6x plus 7. That's how I'm going to write that. And basically, 5 to the power of -1 is 1/5. So 1/5 is equal to -6x plus 7. If you want to clear that denominator, you can multiply everything by 5. So if I multiplied 1/5 by 5, I'd get 1. If I multiplied -6x by 5, I would get -30x. If I multiplied 7 times 5, I would get 35. So at this point, I can solve for x. I'm just going to subtract 35 away from each side of the equation. This will, of course, cancel. 1 minus 35 is -34. This equals -30x. And if I want to get x by itself, I divide both sides by -30. And what's going to happen is this cancels with this, and I'm going to get that x is equal to -34 over -30. The negatives cancel. Each is divisible by 2. 34 divided by 2 is 17. 30 divided by 2 is 15. So let me write this over here. I'm going to say x is equal to 17 over 15. Okay, let's take a look at one more of these. Again, this is very, very simple. You're just using some basic algebra. So we have 5 times log base 6 of -8x minus 6. Then outside we have -4, and this equals 6. Again, you want to get it to the point where it's this guy right here is equal to one number over here. Okay, so to do that, what do I need to do? I need to get rid of this 4 over here. So add 4 to both sides, and that cancels. And then what I'm going to have is 5 times log base 6 of -8x minus 6. And this equals 6 plus 4 is obviously 10. Now to get rid of this 5 over here, that's multiplying this log base 6 of -8x minus 6, then I'm just going to divide both sides by 5. Okay, and that'll take care of that. So this cancels, and this over here is going to be a 2. So now I have it in the format that I want. So log base 6 of -8x minus 6 is equal to 2. So don't let it scare you when you see something long like that. It's not that big of a deal. You just need to go through a few steps to get it into a format that you can do something with. So now we can put this in exponential form to get a solution. So my base is 6, and it's raised to the exponent of 2, and it's equal to what? It's equal to this guy right here, the argument of the logarithm. So -8x minus 6. 6 squared is 36. And let me flip this around. So let me say -8x minus 6 equals 36. Let me scroll down and get a little bit of room going. And let's add 6 to both sides of the equation. That's going to cancel. We get -8x is equal to 36 plus 6 is 42. So this is 42 here. And let me divide both sides by -8 to finish this off. And so this cancels. We get x is equal to 42 over -8. Now I know that's going to be negative. Each is divisible by 2. 42 divided by 2 is 21. And 8 divided by 2 is 4. So you get x equals -21/4. In this lesson, we want to talk about the properties of logarithms. So the first property I'm going to cover is known as the product property for logarithms, or you might hear called the product rule for logarithms. And what we'll say here is that x is greater than 0, y is greater than 0, a is greater than 0, and a is not allowed to be equal to 1. And so this is our property. Log base a of x times y. So this is multiplication here. This is equal to log base a of x plus log base a of y. So this is a really important property, something we're going to use all the time. When you start out with the form on the left and we go to the form on the right, it's known as expanding. Okay, and if we start out with a form on the right and we go to the form on the left, it's known as condensing. And we'll see examples of each at the end of the lesson after we go through the properties. Now, really quickly, I just want to show you some common misconceptions, some trap things that you might be thinking that work but that don't work. So the first one is if you say something like log base a of, let's say, x plus y. So a lot of people get confused, okay, and they say, okay, this is log base a of x times y like this. This is not the same, okay? This is not the same as this, what I wrote up here. Notice that you have log base a of x plus y like this. Over here you have log base a of x plus log base a of y. So don't do this. This does not work out. This is wrong, okay? So that's the first misconception. The second misconception is to take this and think that you can use some sort of distributive property here. So a lot of people will say, okay, this is log base a of x plus log base a of y. This is also wrong, okay? We know that log base a of x plus log base a of y is equal to log base a of x times y. It's not log base a of x plus y. All right, so next we're going to talk about this quotient property, or again, you could say the quotient rule for logarithms. And we have the same restrictions. So x is greater than 0, y is greater than 0, a is greater than 0, and a is not allowed to be equal to 1. So we have log base a of x over y is equal to log base a of x minus log base a of y. So here you've got to pay attention because this guy right here in the numerator goes right here. Okay, so it's in the first position. So it's log base a of whatever's here first in the numerator, then minus log base a of whatever's here in the denominator. In this case, it's y. Okay, so this is how this sets up. All right, the last one I'm going to cover today, and there's more properties, but I'm going to do them in the next video. Again, if x is greater than 0, y is greater than 0, a is greater than 0, and a is not equal to 1, and r is going to be any real number, well, this one is where log base a of x to the power of r is equal to r times log base a of x. So basically what this property allows you to do is take your exponent out in front, okay? So here it's out in front, it's just been pulled down. So this is very useful for us when we're solving equations, and we'll see that in the upcoming lessons. All right, so now that we know the properties, let's jump in and look at some examples. In most cases, these are very, very simple. You'll get a few that are kind of difficult, but most of them are very easy. So we have log base 9 of, we have x to the 6th power times y cubed times z. So we want to expand this, okay? So we're going to use our product property for this, or again, the product rule, however you want to think about that. And the first thing I'm going to do is realize that, again, if this is multiplication in here, I can say that this is log base 9 of x to the 6th power plus, and let me change colors here, log base 9 of this y cubed, then plus, let me change colors again. So we'll have log base 9 of your z, okay? So that's pretty simple. The only thing you want to do in addition to this, if you have these powers here, you want to bring them out in front if you're expanding, okay? So let's go ahead and do that real quick. So I'm going to have 6 times this log base 9 of x now, and then I'm going to have plus, my 3's coming out in front, so 3 times log base 9 of this y, then plus, let me change colors once more, I just have my log base 9 of z, okay? So log base 9 of x to the 6th power times y cubed times z turns into 6 times log base 9 of x plus 3 times log base 9 of y plus log base 9 of z. All right, let's try another one. So we have log base 7 of, and then for the argument here, we have this zx that's raised to the 4th power over y, and then this whole thing is raised to the 4th power. So you just have to be careful here to set this up correctly. Again, we want to expand this. So the first thing I'm going to do, and you could do this multiple ways, but the first thing I'm going to do is apply this exponent here to the z and the x. So I'm going to say that I have log base 7 of z to the 4th power, x to the 4th power, over y, and this whole thing will be raised to the 4th power. Okay, so at this point, what I'm going to do is I'm going to apply the exponent here, this 4, to everything. So I would have log base 7 of, you would have z to the 16th power, right? You just multiply exponents here, z stays the same. Then x to the 16th power, same thing, multiply exponents, x stays the same. This is over y to the 4th power. Okay, so once it's in this format, it's pretty simple overall. And let me just put equals here. Now you have division involved and you also have multiplication involved. So what you can do, and this is helpful so you don't make a sign mistake, and we'll see some examples where you can clearly make a sign mistake in the next example. But what you can do here is just go ahead and say, okay, well, this is my numerator, this is my denominator. So based on our rules, I can say that this is log base 7 of the numerator. In this case, that's z to the 16th power times x to the 16th power, okay? And then I'm going to subtract away log base 7 of the denominator, which in this case is y to the 4th power, okay? So I'm just going to start with this. You can do it a different way, but that's how I'm going to do it. Again, this is going to keep you from making a sign mistake later on when you get to tougher problems. So over here, what I'm going to do is expand this now because I have this multiplication, okay? So to do that, I'm going to say I have log base 7 of z to the 16th power plus log base 7 of x to the 16th power, and then minus my log base 7 of y to the 4th power. Okay, so we're almost there now. Let me put my equals in here. And all I'm going to do is I'm just going to bring these out in front in each case, and we will be done. So the 16 comes out in front. We have 16 times log base 7 of z. Then plus 16 comes out in front. So we have 16 times log base 7 of x. Then minus my 4 comes out in front. So 4 times log base 7 of y. And that's it. So we have 16 times log base 7 of z plus 16 times log base 7 of x minus 4 times log base 7 of y. All right, let's look at another example. And this one's a little bit more challenging. And you'll run into an issue here where you can easily make a sign mistake. So I'll show you how to guard against that. So we have log base 5 of, you have the square root of x squared plus 1 over x cubed times, let me put that multiplication symbol in there so it's clear, the quantity x plus 1 to the 4th power. Okay, so if we want to expand this, let me start by thinking about, first off, if you have a radical with these problems, go ahead and write it in exponential form. So you know if you have the square root of something, it's raised to the 1/2 power. If you have the cube root, it's raised to the 1/3 power, 4th root, raised to the 1/4 power, so on and so forth. So I'm going to first say this is log base 5 of, I'm just going to say that this is, and let me kind of make some parentheses here, and then some inner parentheses with x squared plus 1. This is raised to the 1/2 power. And then down here, I have my x cubed times, again, this x plus 1, this quantity raised to the 4th power. So that's my setup here. Okay, so what I'm going to do is I'm going to think about my quotient property first. That always keeps me from making a sign mistake. So what's in the numerator? This guy right here. So let's start with that. So we'd have log base 5 of what's in the numerator, which is x squared plus 1. Again, this is raised to the 1/2 power. And then I'm going to subtract away, again, you're going to have that log base 5, so log base 5 of what's in the denominator, okay? So in this case, it's going to be x cubed times this quantity, x plus 1 to the 4th power. Here's where you've got to, again, pay attention. You're subtracting this whole thing away. This can be further expanded because you have this multiplication involved. So to not make a sign mistake, what I'm going to do after I set this up, I'm going to put some brackets around this, okay? And I advise you to do the same. I think you should always work with your quotient property first so you can set it up this way, because if you don't, it's very, very easy to forget about the sign and turn in the wrong answer. So let's scroll down a little bit and let's put equals here. And what I want to do now, I'm just going to pull this out in front. So this comes down here. I'm going to have 1/2 times log base 5 of, you've got this x squared plus 1. So this part is done. I can't do anything else. Then you've got minus. I'm still going to have my brackets here. With this, I know that I can expand it because I have my multiplication. So I'm going to have log base 5 of this x cubed. And then plus, you have your log base 5. And let me kind of scroll this over so it fits. So then of this x plus 1. Okay, and this is raised to the 4th power. And then I'm going to close these brackets. Now, I'm not done yet. So let's put equals and let's keep going. I want to pull this down. And I want to pull this down. And I want to distribute the negative to finish this off. So let's first pull those exponents down. So we're going to have that 1/2 times log base 5 of x squared plus 1. And then minus, I'm still going to have my brackets. I'll remove them in a second. So we have this 3 that comes down. So 3 times log base 5 of x now. The 4 comes down. So plus 4 times log base 5 of x plus 1. Okay, so now if you want to remove the brackets, this is what's going to remind you. Again, you're subtracting the whole thing away. So remember, if you do this, if you have minus in front of parentheses or in front of brackets or whatever it is, you've got to distribute that to each guy, each term, okay? So if you get rid of this, everything becomes negative. So this gets distributed to this, and now you're not going to make a silly sign mistake, okay? And what would have happened is if you don't use brackets, the common thing is you just put minus the first thing and you have plus the second thing, and that's where you get messed up and you turn in the wrong answer. Okay, so let me put those brackets back. So basically you want to set it up this way so you end up with a nice clean answer and you don't make a silly mistake and get points off on your test. All right, let's take a look at some examples with condensing now. So in my opinion, these are a bit trickier. They're not that bad overall, but they are a little bit harder than when you expand. So we have log base 8 of x plus log base 8 of y plus log base 8 of z plus log base 8 of w. And this is all over 2. So I want you to realize first and foremost that this is a common denominator, okay? So I could have log base 8 of x over 2 plus log base 8 of y over 2, so on and so forth. So what I'm going to do is consider this as if I had 1/2 multiplied by each one of these guys. And then what I could do is I could just pull it out, right? So I can say that I have 1/2 times inside of brackets or parentheses or whatever you want to use. I would have my log base 8 of x. And then plus my log base 8 of y, and then plus my log base 8 of z, and then plus my log base 8 of w. Okay, so once that's done, what you can do from here is use your product property on the inside. So I can condense this all down to, I'm just going to start with my 1/2 times, then I'll have log base 8, and again, I can condense this down to x, y, z, w, or if you want to write that in alphabetical order, just do w, x, y, z, okay, like that. Now, this guy can come back up here, so we'll say this equals log base 8 of, you'll have your w, x, y, z, and this whole thing, so each one of these guys is going to be raised to the 1/2 power, but instead of doing that, I'm just going to write it with the square root. So I'm just going to say we have log base 8 of, and I'll say the square root of w, x, y, z. All right, let's take a look at one more. And this one's quite tricky just because of the signs. So we have 24 times log base 7 of a minus 4 times log base 7 of b minus 4 times log base 7 of c. Okay, so there's a lot of different ways to do this. If you see this situation, this is how I do it. If you want to choose to make these guys plus -4 and plus -4, and then treat them as negative exponents, that's fine. That'll get you there too. But what I'm going to do is I'm going to factor out the negative in each case. I'm going to just treat that as -1, pull it out. So what I'm going to say I have here is 24 times log base 7 of a. I'm going to pull this minus out. So I'm going to put a minus here, and then inside of parentheses or brackets or whatever you want to use, I'm going to have 4 times log base 7 of b. This will be plus now because remember I pulled the sign out, the negative. So 4 times log base 7 of c. And so inside of here, I know that I can do some additional work, and I can do some additional work over here. So let's do that real quick. And then we'll use our quotient property because we see we have a minus sign. So over here, I know I can bring this back up. So I'm going to start by saying I have log base 7 of a to the 24th power. Okay, you can put parentheses around that if you want to make that cleaner. And then minus, again, inside of these brackets. I'm going to go ahead and pull this up. So I'm going to have log base 7 of b to the 4th power. Then plus, I'm going to pull this up. So I'm going to have log base 7 of c to the 4th power. Okay, so from here, it's not too bad. I'm going to keep this one unchanged. So log base 7 of, you've got your a to the 24th power. Then minus, over here, what I'm going to do, I have my product property I can use. So I've got this addition. I'm going to condense it down and say I have log base 7 of, you've got b to the 4th power and you've got c to the 4th power that are now going to be multiplied together. So I'm going to put b to the 4th power times c to the 4th power, like that. Okay. And now I have my quotient property I can use because, again, I have this minus here. So I have the same log base 7 and log base 7. So that is what I'm going to write first. So I'm going to have my log base 7 and then of. So this guy's going to go in the numerator. This guy's going to go in the denominator. So I'm going to go a to the power of 24 in the numerator, and then over in the denominator, I'm going to have my b to the 4th power times c to the 4th power. Okay. So this is how you want to write it. Make sure you're not putting log base 7 of a to the power of 24 over log base 7 of b to the power of 4 times c to the power of 4. That's another common mistake. Please don't do that. This is how you write this. Log base 7 of this guy in the numerator and then this guy in the denominator. That's all you need to do. In this lesson, we want to continue to talk about the properties of logarithms, and also we're going to move into finding the inverse of an exponential or logarithmic function. All right, so before we can get into finding the inverse of an exponential or logarithmic function, in some cases you're going to need some additional properties, and we need to develop those. And I just want to show you where they come from instead of just kind of giving them to you. So I'm going to start with an exponential and logarithmic function. We know they're inverses. I'm going to prove that they're inverses through function composition. And from that process, we're going to get two new properties that we can use in our lesson today. So we have f of x equals a to the power of x, and we know that a is greater than 0 and not equal to 1. And we have g of x equals log base a of x, and we know that a is not equal to 1, greater than 0, and x, the argument of the logarithm, is greater than 0. All right, so from this, we already know they're inverses, so we can do our function composition. So f of x equals my a to the power of x, and g of x equals log base a of x. We know these guys are inverses. So if they're inverses, we know that f of g of x equals x, and g of f of x equals x. Let's start with this one. So I would take my f of x, which is a to the power of x, and where I have this x here, I'm going to be plugging in g of x. G of x equals this, so this is going to get plugged in right there. So up in the top, for my exponent, I have log base a of x. Now let's stop for a minute and think about this. Why would this equal x? Well, if I take this logarithm on its own and just kind of write it separately, so we can think about this, log base a of x, what happens is this is the base. A is the base. We already know that. Let me kind of highlight this or circle it or put a square around it, whatever you want to say there. So that's my base, and it's raised to a certain power, and I get an answer of x. So really, I can say that log base a of x is the exponent to which this base a needs to be raised to in order to obtain, again, this answer of x. Well, I have a base of a, and it's raised to the exponent here, okay, because this is really just an exponent, required to give me an answer of x, so I just get x. To see an example of this, because I know when you work with this generically, it's quite confusing. To see an example of this, let's suppose that we had 5 raised to the power of log base 5 of 25. What's this going to be equal to? Well, again, think about this separately. Well, log base 5 of 25 is the exponent to which the base 5, again, this base 5, must be raised to in order to obtain an answer of 25. So this is an exponent, it's a value. We know it's 2, but let's pretend we didn't know that. Well, I have 5. It's raised to the power required to give me an answer of 25, so the answer is just 25. Okay, so that's all it is. So in general, when you see, let me just kind of write this as a generic statement over here. When you see a raised to the power of log base a of x, it's just equal to x. So let's now erase this, and let's think about the other one. So now I want to do g of f of x. So g of f of x. And remember, this is going to give me x as well. So now I'm going to plug this thing right here, the f of x, in for x in g of x. So this equals log base a of, and let me change colors here. So you're going to have a to the power of x as the argument of the logarithm. Now, for this one, it's a lot easier to wrap your head around. You already know that from the power property, you can bring this out in front legally. So what I can do is say this is x multiplied by log base a of a. Now, this guy right here represents 1. Why does it represent 1? Well, this is a raised to what power gives me a, right? That's the exponent that this guy represents. A raised to what power gives me a? Well, it's 1. So really, I can just say that this is x times 1, which is just x. So that's another property we're going to be using. We can basically just say, and I'm just going to put it over here, this is just x. We can say that log base a of a is equal to 1. And then also we can say log base a of a to the x power is equal to x. All right, so now that we have those special properties under our belt, let's move on and look at how to find the inverse of an exponential or logarithmic function. So these problems are pretty easy overall. I'm going to start out with f of x equals this log base 2 of 4x. And again, the first thing you want to do is just replace f of x with y. So I'm going to say y is equal to my log base 2 of this 4x. And then I'm going to swap x and y. So instead of y here, I'm going to have x. And this is equal to log base 2 of, again, I have 4x. So now I'm going to put 4y. Okay, so to solve this for y, which is our next step, what I want to do is put it in exponential form. So remember how to do this. This is your base. So your base is 2. Then it's raised to this power. Remember, it's solved for the exponent when it's in logarithmic form. So 2 to the power of x is going to be equal to this guy right here, the argument of the logarithm. That's your answer. Okay, so this is the 4y here. So to solve this for y is pretty simple. I'm just going to divide both sides by 4. And let me kind of scroll down and get some room going. So I'm going to divide both sides by 4. And what I'm going to end up with, and I'm going to flip the sides around so that y is on the left. So I'm going to say y is equal to this 2 to the power of x over 4. Okay, so the only thing you want to do now is just replace y with your f inverse of x. So f inverse of x is equal to 2 to the power of x over 4. Be careful here. The tendency for a lot of students is to think this is 2x over 4. It's not. This is 2 to the power of x over 4. So you can't go through there and cancel a common factor of 2 in case you were trying to do that. Let's take a look at another one. So I'm going to replace my f of x with y. This equals log base 4 of my x cubed. And again, I'm going to swap x and y. So I'm going to put x is equal to log base 4 of y cubed. And now I just want to solve for y. So again, what I'm going to do here is I'm going to put it in exponential form. So I'm going to say that 4 to the power of x is equal to y cubed. So 4 to the power of x is equal to y cubed. Now, at this point, if I want to get y by itself, I just take the cube root of each side. And let me just kind of slide this stuff down so I have enough room to do this. So I'm just going to take the cube root of this side and the cube root of this side. And again, you really can't do anything with this over here other than to say that you have y is equal to the cube root of 4 to the power of x. You could also say you have 4 to the power of x over 3 if you wanted to do that. So you could write this with the exponents and say it's 4 to the power of x over 3. That's equally valid. But again, you're going to change this notation and say you have f inverse of x is equal to 4, again, raised to the power of x over 3, or you could say the cube root of 4 to the power of x. All right, let's take a look at another one. So I'm going to replace, again, my f of x with y. So this equals my log base 4 of, you've got your 5 to the power of x minus 6 all over 4. And again, I'm going to swap x and y. So to do that, let me kind of scroll down a little bit. I'm going to say I have x equals my log base 4 of 5 to the power of y minus 6 over 4. And then from here, again, I'm just going to put this in exponential form. So I'm going to say 4, the base here, raised to the power of x. So 4 to the power of x is equal to this guy right here. So you have 5 to the power of y minus 6 over 4. Now I want to solve for y. And so to do that, I can clear the denominator here by just multiplying both sides by 4. But you have to be careful here. This is 4 to the power of x, so it's not going to be 16 to the power of x. You just want to say, I'm just going to multiply this side by 4 and this side by 4. It's basically just 4 times 4 to the power of x, okay? So don't say that's 16 to the power of x. That's a common mistake. So we want to cancel this out, and I'm just going to say this is equal to 5 raised to the power of y minus 6. And then basically what I want to do now is add 6 to both sides of the equation. Let me kind of scroll down a little bit more. And so from here, I'm going to have 4 times my 4 raised to the power of x, and then plus my 6. And this equals, over here, this is going to cancel. I have 5, and I'll write this over here, 5 to the power of y. So now here's where we can use one of our properties we learned earlier. If I want to get this y to come down, I can basically use any log to do that. But if I use log with a base of 5, you do this, log base 5 of 5 raised to the power of y. We learned earlier, this is just going to be y, okay? So I'm going to do that to both sides. Let me scroll this a little bit down to fit this. So I'm going to say I have log base 5 of this whole thing. And we know that log base 5 of 5 is 1, so this is just y. So I'm going to flip the side that this is on. It's going to come to the left now. So I'm going to say that this is y is equal to, over here, I'm going to have log base 5 of, I'm going to clean this up a little bit. I want you to realize that this is 4 to the first power times 4 to the power of x. So by the rules of exponents, I know that if I have the same base and I'm multiplying, I can add exponents, right? I keep the base the same, so 4 would stay the same, and I would add the exponent of 1 to the exponent of x. So I would say this is 4 to the power of 1 plus x or x plus 1, however you want to write that. I'm just going to put x plus 1, and then we would have plus 6 like this. So this is going to be your answer. I'm just going to take the y away and say this is f inverse of x. All right, let's look at another one. So again, I'm just going to change this to y. So y equals 10 to the power of x, and then minus 5. And again, I just want to swap x and y. So this would be x, and this up here will be y. And then from here, I just want to solve for y. Let me scroll down and get some room going. So I want to say that I have x is equal to, I'm going to add 5 to both sides of the equation. Go ahead and get rid of this. So I'll say x plus 5 is equal to 10 raised to the power of y. Now I want to get this y on one side by itself. Right now it's as an exponent. So to get rid of that, again, I'm just going to use a log with a base of 10. And in the next lesson, we'll learn this is the common log, so I can just write log. But for right now, I'm going to go log base 10. So I'm going to go log base 10 of this left side, so x plus 5, is equal to, you're going to have the log base 10 of 10, okay, raised to the power of y. Let me make that more clear. And what happens is log base 10 of 10 raised to the power of y is just y. Let me make that better. So this is a y. Okay, so if I scroll down, get some more room going, what I have is log base 10 of x plus 5 is equal to y. And I can just replace this at this point and say this is my f inverse of x. All right, I saved the best one for last. This is an example of one that gives students a lot of trouble. There's a lot of different techniques to solve it, okay? And if you attempt this one on your own, I advise you to pause the video and try it on your own at first and struggle with it. And if you can get it on your own, that's great. If not, we can go through the solution right now. So again, the first thing I'm going to do, same as always, I'm going to say that y equals 4 to the power of x plus 1, okay, over 4 to the power of x. I'm going to swap x and y. So let me scroll down a little bit. I'm going to need a lot of room for this. So I'm going to put x is equal to, I'm going to have 4 raised to the power of y plus 1, then plus 1, then over 4 to the power of y. So I've got a y here, and I've got a y here, okay? So the first part of this that's tricky is, if you're not used to working with exponents, remember what this represents here, okay? If I have 4 to the power of y plus 1, this is really, let me kind of write this off to the side. If I had 4 to the power of y times 4 to the power of 1, we saw this earlier, this is 4 to the power of y plus 1. Okay, so you've got to be thinking this way when you see problems like this, because you're expected to know this and to be able to kind of break it back up. So what I'm going to do, let me kind of scroll down, get a little room going. I'm going to use that. So x equals, I'm going to have 4 raised to the power of y, and then I'm going to have times 4 raised to the power of 1, and then this is plus 1, and this is over 4 to the power of y. Now, At this point, you have a lot of different roads or a lot of different paths that you can take. The path that I'm going to take, the one that I find the easiest, is I'm going to make a substitution. You don't need to do this, but I am most comfortable doing this, so I'm going to show you this, and I think it'll help you. So I'm going to, over here, say that we're going to let u be equal to 4 to the power of y, okay? So u equals 4 to the power of y. What I'm going to do is say I have x is equal to u times 4 plus 1, and this is over u. So now I'm just going to solve for u. That's very easy to do. It's not complicated at all. We've been doing it forever. So let's scroll down. And I'm just going to multiply both sides by u to get this thing started. And so I multiply by u over here and by u over here. This cancels. So you get xu or ux, however you want to think about that, is equal to, you're going to have 4u plus 1. Okay, if I want to solve for u, I got to get all the terms with u on one side. So let me subtract 4u away from both sides of the equation, and I'm going to run out of room. So let me copy this and go to a fresh sheet and just paste this in. And what I want to do here, I want to have minus 4u and then plus xu is equal to, this cancels, the number 1. Okay, so I'm going to factor the u out. So I'm going to have u, and then in the parentheses, I can write negative 4 plus x, or I can switch that around and say x minus 4, which is what I want to do. And this is equal to 1. Okay, so I'm going to divide both sides by x minus 4. Okay, and now I have this in terms of u. Okay, so I have u is equal to 1 over x minus 4. Now, we're not done because remember, I made a substitution. I said u is equal to 4 to the power of y. So at this point, I can erase this and just say that this is 4 to the power of y. From here, I know I can just use log base 4 on both sides, and I'll be done. So let me just move this over, and I'll say that I have log base 4 of this guy. And let me slide this over, and I'll say I have log base 4 of this guy. Okay, so we know that this is just going to come down, and this part's 1. So I get that y is equal to log base 4 of 1 over x minus 4. Okay, and this I can replace with f inverse of x, and I'm done. Okay, so I get f inverse of x equals log base 4 of 1 over x minus 4. In this lesson, we want to talk about common and natural logarithms. Additionally, we're going to talk about the change of base formula for logarithms. Now, most of you already know that the log key on your calculator corresponds to a logarithm with a base of 10. This type of logarithm is known as the common logarithm, and when we write the common logarithm, we can use a little shorthand and not include the base. So something like log base 10 of x can be just written as log of x. So when you use this key on your calculator, again, you have to understand that the base is 10. So something like, let's say, log of 100, okay? If you type that into your calculator, log, and then for the argument, just put 100, this is going to give you a result of 2. And again, the reason is because this is log base 10 of 100, and 10 to the second power, or 10 squared, gives me an answer of 100. So this guy has a value of 2. All right, so additionally, most calculators also come with this ln key. So this ln key represents the natural logarithm. So this is going to be a logarithm with a base that's our special number e. So this guy right here. So you remember the special number e, about 2.718. We talked about this earlier in the chapter when we were looking at different compound interest scenarios. So it turns out that the natural logarithm comes up a lot when you have problems that involve growth or decay. So you'll see this a lot in science class. You also see it a lot in math class, economics class, things like that. So log base e of x, we can write this in a shorthand notation by saying ln for the natural log of x. And if you wanted to calculate the natural log of some number, let's say 15, for example, you'd hit the ln key on your calculator, and then when the parentheses come up, just put 15 in, okay, and hit enter. And in this case, you get approximately, because this is an irrational number, 2.708. So 2.708. 0.08. And again, I'm rounding this. In a lot of situations, you're going to have to round things because you're going to get an irrational number. All right, so now what I want to do is go into this change of base formula for logarithms. And this is useful because, again, most calculators just have the log key and the ln key. I know that nowadays, some of the TI-84s and the TI-89s and, the upper end calculators do let you punch this in directly and get an answer, but it's still useful to know the change of base formula. So let's say I start with log base 2 of 3, and I don't know what it is, so I just say it's equal to x. Okay, from here I can put this in exponential form, so 2 to the power of x is going to give me 3. 2 to the power of x is going to give me 3. So I have the log key available to me on my calculator. So let's say I take the log of both sides, and again, this is a logarithm with a base of 10. So log of this side and log of this side. So this comes down from our power property. So we get x times log of 2 is equal to log of 3. Okay, so how do we solve for x? Well, we already know how to do this. We just divide both sides by what's multiplying x. So in this case, it's log of 2. Okay, nothing's changed. So log of 2 over here. And basically, this is going to cancel, right? That's gone. So I get that x, or the value of this guy, is going to be equal to log of 3 over log of 2. And I can calculate this using my calculator, right? So this is approximately, because I'm going to have to round here, it's an irrational number, I would say 1.585. So 1.585. With that being said, let's take this process and dive into a general formula. So we don't need to set it equal to x each time and go through this complicated thing. What you'll realize is that it works out the same way each time. So what you can do, if you have log base a of x, where x is the argument and a is the base, well, you can say this is equal to log of some base b of x over log of some base b of a. Well, in our case, I just chose a base of 10 here, okay? And so I said log of x over log of a. Remember, this was 3 and this was 2. So this was 3 and this was 2, right? We found our answer by saying log of 3 over log of 2. So log base 10 of 3 divided by log base 10 of 2 gave us our answer. And again, that was about 1.585. Again, generally speaking, that's all you need to do. And your restrictions here are as expected. We have that a is greater than 0 and not equal to 1. Well, a is the base here and the argument there. Then b is greater than 0 and not equal to 1. That's your base here and here. Again, that can be whatever you want. Usually you're going to use a base of 10 or a base of e, so you can use those two kind of buttons on your calculator, the ln key or the log key. And then x here and here, that's got to be greater than 0 because in each case it's just an argument. So let's just blow through a few of these. It's a very easy process. Log base 4 of 12 is equal to what? Again, I'm just going to use the common logarithm. So I'm going to go log of 12. Okay, so log of the argument here, that's what comes first. And then over log of the base, okay, that's what comes second. So the base is 4. And this would be approximately, because again, you've got an irrational number here, I'll say about 1.792. All right, let's look at another one. So we have log base square root of 5 of square root of 8. So again, all I'm going to do, this looks kind of hard, but it's really the same thing. You just punch it into a calculator. And I'm going to use the natural logarithm. So I'm going to go the natural log of, again, this argument here, so square root of 8. And then over, you're going to have the natural log of, again, square root of 5. So all you need to do is hit the ln key, square root of 8, divided by ln key, square root of 5. And you're going to get approximately 1.292. All right, let's look at one more of these, and then I'll show you something else. So we have log base 1/5 of 20. So again, to set this up, I'm going to say this is what? You can use ln, the natural logarithm, or you can use log, the common logarithm. Either one of those keys will be available. So I'm going to use the common logarithm. So log of, again, the argument here, so 20, over log of, again, I'm going to use this base here, so 1/5. And then, so this guy right here would be approximately, well, you type that into your calculator, you're going to get about negative 1.861. All right, so in addition to those easy problems, we also get these kind of multiplication scenarios that come up. And these problems typically involve you needing to realize that you can simplify in some way. So let me go through one of these as a typical example. So we have log base 3 of 4 times log base 5 of 9. So the very first thing you want to do is set up each with the change of base formula. So I'm just going to use my common logarithm. I'm going to say the first one is log of, again, the argument there of 4 over log of, again, the base there is 3. Then times, for this one, it's going to be log of, again, the argument is 9 over log of, again, the base is 5. Now, before you go any further and start typing this stuff into your calculator, you need to look and see if there's anything you can simplify, because a lot of times they want you to show that, okay? So here, I know that I have a base of 3. Let me just highlight that. And here I have a base of 9. So I know that 9 is 3 squared. So the first thing you need to realize is that you want to rewrite this as 3 squared like this. And then from your properties of logarithms, this guy can come out in front. So basically you can erase that and just put a 2 out here. Now, you see that this is just multiplication involved here. So there's nothing stopping me from canceling this with this because those are common factors. Log of 3 over log of 3 is the same non-zero number. So you can cancel those, okay, and the result will be 1. So you're meant to show that this will be simplified to basically 2 times log of 4 over log of 5. And sometimes these will work out perfectly to be a rational number, but in this case, it's not going to be, so we'd still have to type this into a calculator, and we would get approximately 1.723. But just be on the lookout for these, because in a lot of cases, they'll give you a problem and say, show how you could simplify this, and they mean that you need to go through and cancel things like we did here. In this lesson, we want to talk about solving exponential equations using logarithms. So at this point, we already have all the tools that we need to solve any exponential equation that we come across. So I'm just going to start out with an easy example. We'll see some harder examples as we progress through the lesson. So we have 10 raised to the power of negative 2x, and then we have plus this 6, and this is equal to the number 18. All right, so how could we solve this? Let me just rewrite it. So 10 raised to the power of negative 2x. Then we have, again, plus 6, and this equals 18. Well, the first thing you want to do, if you're solving for x, you want to isolate the term that contains x in it. So this guy right here is the term that contains x in it. So to isolate that, I would just subtract 6 away from both sides of the equation. So that's the very first thing you want to do. So this cancels. All right, so now on the left, I have this 10 raised to the power of negative 2x. And this is equal to 18 minus 6 is 12. Now from this point, here's where you have to think about your logarithms that you worked with. You know that you have the power property for logarithms, and basically that allows you to take your exponent down out in front, okay? So what I want to do is use that property here so that I can get this guy to come down, okay? So if I take the log of the left side, and I also take the log of the right side to make that legal, what's going to happen is from my power property, this guy right here can now come out in front, okay? So let's scroll down and get some room going, and we'll see this real fast. So we're going to have our negative 2x out in front. We'll make that negative just a little bit better. And then times this log of 10. Now, this is 1, and I'll cancel that in a minute. I want to explain why it's 1. I think most of you know that already. But this is equal to log of 12. Now this is 1, so you can just cancel it and put 1. The reason it's 1 is, remember, when you have log of something, you don't show a base. It's because you have the common logarithm. The base is understood to be 10. So if I showed you that you had log base 10 of 10, again, what is this? This is equal to 1 because 10 to the first power gives me 10. So if this is 1, then really this left side is just negative 2x, because negative 2x times 1 is just negative 2x. And now this is equal to log of 12. And once we get it to this point, it's really, really simple. Log of 12 is just a number, so don't let that scare you. Basically, all you want to do is divide both sides by negative 2, just like we've always done, okay, to isolate x. And so we know that this right here is going to cancel, and I have x by itself, and it equals my log of 12 over my negative 2. Now, this is the answer if you don't want to give an approximation. If your teacher says, hey, I want the exact value, then you give this, log of 12 over negative 2. Now, if you wanted to approximate this using your calculator, that's fine too. Generally speaking, you're going to have some specific decimal place that you're going to want to round to, and the teacher will let you know that in your assignment. So I'm going to punch this up on a calculator, and I'm going to get about, and I'm going to use my approximate sign there. So negative, and then I'm going to say 0.5396. And again, I'm rounding this guy. And again, I'm using the approximation symbol there to show that it's a rounded amount. It's an approximation. It's not the exact amount, but it's pretty close. All right, let's take a look at a harder example, or I'd say a more tedious example. So now we have 3 multiplied by 4 raised to the power of 3 minus 8x. Then we have minus 4, and this is equal to 30. So again, the first thing I want to do, since x is here, I want to isolate this guy, okay? So to do that, I have multiplication here and I have subtraction here. Let me add 4 to both sides of the equation to get things started. I know that this will cancel. And on the left side now, I have 3 multiplied by 4 raised to the power of 3 minus 8x. And this equals 30 plus 4 is 34. Okay. So from here, again, if I'm trying to isolate this guy, well, what do I have? I have multiplication here. So to undo that, I'm just going to divide both sides by 3. And now this is going to cancel here. And what I'm left with on the left is what I wanted to isolate. So I have 4 raised to the power of 3 minus 8x. And this equals my 34 over 3. Okay. So from this point, I've got to find out how I can get this variable down. Okay, and to do that, again, we're going to use our power property for logarithms. So I'm just going to take the log of both sides. So I'm just going to go log of 4 raised to the power of 3 minus 8x. And this will be equal to log of, you have your 34 over 3, or 34 thirds if you want to say it that way. Okay, so from here, this can come down, right, from the power property. So you have your 3 minus 8x times your log of 4. Now, I want to caution you against something. It's very important that you use parentheses here because this is a quantity, 3 minus 8x, and it's being multiplied by log of 4, which is just a number. So we'll say this is equal to log of, again, 34 thirds. Now, let me make this a little better, a little cleaner. So 34 thirds. Okay, so at this point, you can do this 2 different ways. You can use your distributive property here. So you can multiply log of 4 by 3, and then log of 4 by negative 8x. You can do it that way. Or you can get rid of this guy right now by dividing both sides by log of 4. And that's what I'm going to do. You'll get the same answer either way, so it doesn't really matter. So let's go ahead and cancel this with this. And let's scroll down now. So I'll have 3 minus 8x, and you can drop the parentheses. You don't need them anymore. And then this is equal to, you've got your log of, you've got this 34 thirds. And then this is divided by log of 4. All right, so from here, what we need to do is, again, isolate this x. So I'm going to start by subtracting 3 away from each side of the equation. So I'm going to subtract 3 away from here. That's going to cancel. And subtract 3 away from over there. So now I have what? I have negative 8x is equal to this log of 34 thirds. And this is over my log of 4. And then over here I have minus 3. Okay, so to finish things up, I'm just going to, again, try to solve for x. And to do that, just like we've been doing forever, I want to divide both sides by negative 8. But really, an easier way to think about this here, because we have a fraction involved, I'm going to multiply both sides by negative 1/8. Okay, so that would be the same thing. Make sure you use parentheses here, so times negative 1/8. This, of course, is going to cancel, and on the left, you just have your x that you're looking for. On the right, I'm going to distribute this to each, and so what's going to happen is, for the first one, I'm going to have the negative of log of 34 thirds over, you're going to have this 8 out in front times log of 4. Okay. Then what do we have? We basically have negative 3 times negative 1/8. So that would be what? That would be plus 3/8. So this is going to be your answer. Again, if you don't want to give an approximation, you would basically say that x is equal to the negative of log of 34 thirds over 8 times log of 4, plus you have your 3/8. Now, if you wanted to give an approximation, you're going to get about, okay, and I'm going to bring this down here because I'm going to run out of room. We're going to say 0.1561. So again, here's your approximation, and here's your exact value. Again, the negative log of 34 thirds over 8 times log of 4 plus 3/8, and then as an approximation, 0.1561. All right, let's take a look at another one. So we have 7 raised to the power of x plus 2 is equal to 2 raised to the power of 2x minus 1. So this one is a little bit quicker to do, but you do have some things that kind of trip you up on this. There's nothing really to do other than to take the log of both sides to start, because you've got to get these guys down, okay? You can't solve it the way it is. So you go log of 7 raised to the power of x plus 2, and this equals log of, you have 2 raised to the power of 2x minus 1. And let me slide this down so it's in the middle of the screen. And so now we know that those exponents can come down. So legally I can say that this is what? This comes down, this comes down. So we have this x plus 2. Again, this is a quantity, so I'm going to use parentheses, times log of 7 equals, this comes down, so the quantity 2x minus 1 times log of 2. So again, here's where I'm going to use my distributive property. You've got to get everything with an x on one side so you can factor that out and solve for x. So I'm going to go and distribute this to each term here. So I'm going to have x times log of 7, then plus 2 times log of 7. And this equals, over here, I'm going to have 2x times log of 2. Let me slide this down so I don't run off the screen. And then I'm going to have minus 1 times log of 2, which is just log of 2. Okay, so now what I want to do is get all my terms with x involved to one side. Okay, so I'm going to have this guy right here and this guy right here. Everything else you want on the other side. Again, the reason you're doing this is so you can factor the x out and then solve for it. So what I'm going to do is subtract 2 times log of 7 away from each side of the equation. And I'm going to subtract 2x times log of 2 away from each side of the equation. So let me do that over here. So minus 2x times log of 2. Okay, and so this guy's going to cancel. And this guy's going to cancel. And what do I have? Well, my new left side is going to be x times log of 7 minus 2x times log of 2. Let me scooch this down a little bit. And this will be equal to, my right side will be what? I'm going to say that I have the negative of log of 2, and then minus 2 times my log of 7. Okay. So how do I solve for x? Again, I want to just think about factoring it out. So if I factor out an x from here and here, what would that leave me with? So this comes out, so I have x out in front. And inside the parentheses, I have the log of 7 minus, you're going to have this 2 here times this log of 2 here. So I would have log of 7 minus 2 times log of 2. Okay. And let me put some closing parentheses there. And this will be equal to, again, over here, this isn't going to change. So we'll have negative log of 2 minus 2 times log of 7. All right. So now, how can I get x by itself? Well, this guy right here is just multiplying x. So all I have to do is just divide both sides by this. So divide by log of 7 minus 2 times log of 2 on both sides. So log of 7 minus 2 times log of 2. And what do we get? Well, this cancels, so that's done. We get x is equal to, we'll have that negative log of 2 minus 2 times log of 7 over log of 7 minus 2 times log of 2. So again, this is your exact answer. If you want to give an approximation, I'll just give one here as an approximate value, and let me make that sign a little bit better. So you punch that into your calculator, you're going to get about negative 8.1931. Again, that's just an approximation. All right, let's go ahead and take a look at another example. So we have e raised to the power of x squared equals 144. So for the previous examples, I used the common logarithm, or again, the logarithm with a base of 10. That's the log key on your calculator. Now I'm going to use the natural logarithm, the ln key on your calculator, because whenever you deal with this special number e, remember, if you type ln for the natural logarithm into your calculator, and then you hit e as the argument, you're going to get a value of 1, right? Because this ln, this represents a log with a base of e. And then if it's of e, this is what? E to the first power gives me e. So that's why this has a value of 1. So what I'm going to do here is I'm going to use the natural log for each side. So this ln is how you want to write that, of e raised to the power of x squared. And then again, for the natural log on this side, write the ln and then of 144. And so this can now come down. So I'll say I have x squared times, if I have the natural log of the number e, this is 1, okay? And this equals, again, the natural log of 144. Okay, so from this point, what do I have? I have that x squared is equal to the natural log of 144. And how can I get x by itself? Well, I just take the square root of each side. So I take the square root of this side. Let me make that better. So the square root of this side, and then remember, you got to do your plus or minus the square root of this side. Okay, so we know that this on the left is just going to be x now, and this equals plus or minus the square root of this natural log of 144. Once again, this is going to be the exact answer. So you have plus the square root of the natural log of 144, and then you have minus, or the negative of, the square root of the natural logarithm of 144. So that's the exact value. If you want an approximation, okay, you can type this into your calculator, and you're going to get approximately plus or minus, we'll say 2.2293. Let me make that a little better. So 2.22, again, 93 is a good approximation for this. All right, what I want to do now is look at a typical word problem that you're going to see in this section. And basically it goes like this. We have how long will it take for money in a savings account that is compounded continuously at 3% annual interest to double? So this is a very simple word problem to solve, but a lot of times if you haven't seen it before, you might get tripped up. So the first thing is to remember the formula for the continuous compound interest. So that's the A is equal to P times the special number E raised to the power of R times T. So again, the R is the rate as a decimal. We have that here, it's 3%. So you're going to plug that in there. So let me just do that now. So let me put this as 0.03 and then times, again, that T. This is your time in years, your time in years. Okay, so remember that. Now, when we think about the rest of this, we have P, which is the principal, and we have A, which is the account balance in the future, or you could say the future value of the account. So typically for these problems, you're given an interest rate, you're given a time in years, and you're given a principal, a starting amount. You don't really have any of that here. Okay, so that's what trips people up. What you have to realize is that you're trying to figure out how long it's going to take for the money to double. So you're going to be solving for T here, okay? And in order to get A and P to behave in this problem, you really have to think about writing A in terms of P, okay? So again, you're trying to double your money. So whatever you put in for P, you're going to have double that for A when this happens. So this is going to be 2 times whatever P is. So once you realize that, once you get past that roadblock, the rest of this is super easy. You're just going to divide both sides by P, and I made that a little too long. So let's divide both sides by P. And we know that this would cancel and this would cancel. And from here, it becomes very, very simple. We have 2 is equal to e to the power of 0.03 times this variable t. Okay, so from here, let me move this down a little bit. I'm going to take the natural log of each side. And the reason I'm going to do that is, again, I'm working with this special number e. So I'm going to say the natural log, or again, use the ln of 2 is equal to the natural log of this side, which is e raised to the power of 0.03 times t. Okay, so from this point, I know that this can come down. So let's come down here, and we'll say what? We have the natural log of 2 is equal to my 0.03 times t, and then times what is the natural log of e. We know that this guy is 1. Okay, so that's going to cancel. So what I have now is that t is going to be equal to what? Well, this is multiplying t, so I just divide both sides by 0.03, and I am done. So very, very simple overall. We can say that t, or the time in years, is equal to the natural log of 2 over 0.03. Now, this was a word problem, so if you give this as an answer, it's basically going to be nonsense, right? You need to give an approximation here. And depending on how precise you want to be, I would round this and say that it's about 23 let's just go ahead and say 10. That's pretty close. Again, you can add more decimal places if you need it to be more precise, but that's pretty much up to you or your teacher and how they assign the question. So let's take this 23.10 and make a little sentence. And I'm just going to say that the money will double in, and I'm going to use about because it's an approximation. So 23.1, and you can put 0 if you want, but 23.1 and 23.10 are the same. Let's just put 23.10 years. In this lesson, we want to talk about solving logarithmic equations. All right, so we're going to start out with an easy example. So we have that negative 9 times log base 11 of negative 4x plus 2 plus 4 equals negative 5. So when you see something like this with just one logarithm involved, you should be thinking about simplifying things and basically trying to get this into exponential form. That's how you're going to solve this type of equation. So what I'm going to do to kick things off, I'm just going to subtract 4 away from each side of the equation. So what's going to happen is that would cancel over here. On the right side, I would now have negative 9 because negative 5 plus negative 4 or negative 5 minus 4, if you want to think about it that way, would be negative 9. On the left side, I would have that negative 9 times log base 11 of this negative 4x plus 2. Okay, so from here, what do I want to do now? Well, notice how you have this negative 9 here that's multiplying this log base 11 of, again, this negative 4x plus 2. So to get rid of that, because this is multiplication, I can use division. So I'm going to divide both sides by negative 9, and that'll clean this up further. So this is going to cancel. And on the left, I'm just going to have that log base 11 of, you've got that negative 4x plus 2. On the right, what do I have? Negative 9 divided by negative 9, that's going to be 1. Okay, so let's scroll down and get some room going, and we'll look at what we have here. Now, I'm going to write this in exponential form. So I'm just going to take this base here, and I'm going to raise it to this guy right here, this 1. So we have 11 to the first power, and this will be equal to this guy right here, this negative 4x plus 2. Now 11 to the first power is just 11, so you can erase that if you want. And basically you just want to solve this very simple equation to get our solution. So what I'm going to do is just subtract 2 away from both sides. So I'll have 11 minus 2, which is positive 9. So 9 is equal to negative 4x. And what I want to do now to get x by itself, again, I have this negative 4 that's multiplying x. So let's divide both sides by negative 4. And of course, now this cancels with this. And I'm going to have that x is equal to, you've got 9 over negative 4, which is basically negative 9/4. Now let's stop for a minute. When you work with these kind of logarithmic equations, you always want to check your solutions and make sure they're valid in the original equation, okay? A lot of times when you're working with these, you're going to get solutions that violate the domain, okay? And so you've got to reject those solutions. So let's go ahead and check this real quick. I'm just going to tell you in advance this one does work out, but you'll see some in this lesson that don't work. So let me erase everything real quick. So again, we have that x is equal to negative 9/4. So I'm just going to plug that in right here and see what happens. So we have negative 9 times log base 11 of negative 4 times negative 9/4. Let's do that off to the side. Negative 4 times negative 9/4. We know the 4s would cancel, the negatives would cancel, and you'd have 9. So this would be 9 plus 2, which is 11. And let's just erase this real quick. And then we have plus 4, and this equals negative 5. What is log base 11 of 11? Well, again, 11 to the first power would give me 11. So log base 11 of 11 is just 1. So let's put a 1 here. Now, negative 9 times 1 is just negative 9. And negative 9 plus 4 would give me negative 5. So it does take a few minutes to kind of check things, but you always want to make sure that your solution works out and also that you don't have a domain violation. If you do, if you plug something in there and you end up with taking the logarithm of a negative number as an example, you want to reject that solution. Let's take a look at kind of a harder example, and I will say harder, but it's just a little bit different in the way that you solve it. You have a log base 7 on each side of the equation. So if I have log base a of x is equal to log base a of, let's say, y, this implies that x is equal to y. So we have a logarithm with the same base on each side of the equation. They're set equal to each other. So you can just say that x is equal to y in this circumstance. So that's what we're going to use here to solve this equation. So we have that log base 7 of 3x equals log base 7 of 70 minus x squared. Again, notice how you have the same base on each side. They're set equal to each other. So you don't have to do anything else other than just say that I have 3x here is equal to this guy right here, which is 70 minus x squared. So this is what we want to solve. So to make this simpler, I'm just going to move everything to the left-hand side. So if I add x squared to both sides, I get x squared over here, then plus 3x, and then if I subtract 70 away from both sides, I'd have minus 70, and this equals 0, okay? So from this point, I can solve this using factoring, or I can use the quadratic formula, or I can even complete the square if I want. It doesn't really matter, whatever you want to do. I'm just going to solve it with factoring because it's usually the fastest. So I'm just going to factor this and say this is x, and it's going to be, let's see, plus 10, and then x minus 7, and this equals 0. Okay, so from here, I'm going to set each of these equal to 0. So I'm going to say x plus 10 equals 0. Of course, the solution here is that x is equal to negative 10. And then here, if I say x minus 7 equals 0, of course, the solution is x equals 7. So these are the two proposed solutions, x equals negative 10 and x equals 7. So here's going to be an example where we have a domain violation and we've got to reject one of the solutions. So let me erase everything real quick. And now let's look at these more closely. So when we work with negative 10, we'll see we have a problem. Let's say I had 3 times negative 10, that's negative 30. So log base 7 of negative 30, again, this is undefined. You don't even need to plug anything else in. Once you see that it fails somewhere, just reject the solution and move on. So this is rejected, so that's not a possibility. So now I can try 7, and I can say, okay, I have log base 7 of, what is 3 times 7? That's 21. And this equals, you have log base 7 of, 7 squared is 49, and 70 minus 49 is 21 as well. So this one does work out as a solution. All right, let's take a look at another one. So we have log base 5 of 9 plus log base 5 of 2x squared plus 3, and this equals 3. So for this type of scenario, you want to turn to your properties of logarithms. Notice that you have the same base here in each case, and you have this addition involved. So we already know that we can manipulate this into one logarithm, right? We can condense. So what we're going to do here is say that we have log base 5 of, remember, if it's addition, you're going to turn it when you condense it into multiplication. It's going to be this guy right here times this guy right here. So 9 times the quantity, make sure you use parentheses, 2x squared plus 3, okay? And let me put another parenthesis there, and this equals 3. Okay, so let's go through and figure this out. We have log base 5 of 9 times 2x squared is 18x squared. And then plus 9 times 3 is 27. Okay, so this equals 3. So from here, all I want to do is just write this in exponential form, and I can very easily get a solution. So 5 to the third power, which is 125, will be equal to the argument here, this guy, this 18x squared, 18x squared plus 27. So what I'm going to do is I'm going to subtract 125 away from each side of the equation. And what is that going to give me? I'm going to have that 18x squared minus, you do 27 minus 125, you're going to get negative 98. So that's why I have minus 98 there. And this would be equal to 0, okay? So from here, you can use the quadratic formula if you want, but it's quickest to realize that you have the difference of squares if you factor out a 2, okay? So if I take a 2 out, I would have 2 times the quantity. From 18, I pull out a 2, I get 9, then times x squared, and then minus. If I pull out a 2 from 98, I get 49. And of course, this equals 0. And once you see it like this, you realize that it's the difference of 2 squares. So we can factor this very quickly using our formula. We say this is 2 times the quantity 3x plus 7 times the quantity 3x minus 7 Of course, this is still equal to 0. So from here, what we're going to do is set each factor with a variable involved equal to 0. So I'm going to say that 3x plus 7 equals 0. Subtract 7 away from each side of the equation. You get 3x is equal to negative 7. Divide both sides by 3. And one proposed solution would be that x is equal to negative 7/3. So let me erase this so we have a little room. And I'll write this up here. I'll say x is equal to negative 7/3. And then for the other guy, I'm going to say that 3x minus 7 is equal to 0. And I'm going to add 7 to both sides of the equation. And I'll have that 3x is equal to 7. Divide both sides by 3. And I'm going to get that x is equal to 7/3. Now, in the interest of time, because I don't want this to go on forever and ever and ever, I'm just going to tell you in advance that both of these solutions are going to work. They're valid solutions. But again, when you're solving logarithmic equations, you've got to stop. You've got to check. Okay, you got to make sure that you don't end up with a domain restriction. I've already checked this, so in the interest of time, we're just going to move on and say our solutions are going to be x equals negative 7/3 or 7/3. Let's go ahead and look at one more example. Again, this is a very easy topic. Most of these can be solved within just a few minutes. Usually the checking is what takes the longest because sometimes you run into some messy things that you have to work with. All right, so we have log base 9 of, you have negative 3x minus 3, then minus log base 9 of 4, and this equals 1. So I have a minus here, and again, I've got log base 9 and log base 9. So again, when I try to condense this into one logarithm, because there's a subtraction sign, I'm thinking about division. So I'm going to have my log base 9 of, this first guy here is going to be the numerator, so negative 3x minus 3. This will be over. The second guy is my denominator, and this all will be equal to 1. Okay, so how do we solve this? We put this in exponential form. So 9 to the first power, which is just 9, is equal to this guy right here, this negative 3x minus 3. This is over 4. All right, so let's solve this real quick. It's very easy. We just multiply both sides by 4 to clear the denominator. So you're going to get what? Multiply by 4, multiply by 4. This cancels. You get 36 equals negative 3x minus 3. You can add 3 to both sides of the equation. And so you're going to get that 39 is equal to negative 3x. Let's go down and get a little bit more room going. And I'm going to divide both sides by negative 3. And what do I end up with? This cancels. I get x is equal to negative 13. Let me make that a little bit better. So x equals negative 13. So that's going to be our solution. Again, I've already checked this. If you want to go back, pause the video, you'll see that it does work out as a solution.